I had this duplicated. That was it. That was it. So
All right.
That's good. Yeah.
Welcome to C++. Now that you guys kind of got your hands dirty, what's your initial thought?
It's
Good.
it's a lot better when you're finishing it. That's when you realize that like it's a lot simpler than you think it is.
Mhm.
You kind
So-
of go in thinking it's hard, but then you realize it's not.
So here's the secret, and nobody tells you these things, right? When you code, or let's put, I'm gonna put it all on me. I'm not gonna say it's about anybody else.
Mhm.
Oh my God, I don't know what I'm doing. I'm so scared. They're gonna find out that I'm a phony and I'm gonna get booted out of the program or booted out of the job, right? Then you start to slowly and slowly dig your way out of it. And then what happens is you finish it. And you take about a whole 5 minutes, or like, good job. Then you go right into another part that you're scared again, and you go through the whole, cycle kind of process in your head, like, oh my God, I'm scared, this is scary, whatever. And I would like to say it gets better. But what you do is you start to just live with it. You're kind of comfortable with the uncomfortable, right? So I have a friend who's a SEAL, right? And he's like going, oh, well, when we go to training, we can just freeze. We're okay with freezing.
Yep.
We sit in water, it's frozen, it's in the ocean, your body temperature is going low, you actually will die, it's that cold. He goes, and we just do it all the time. And it sucks. He goes, but then you get used to the suck
Yep.
and you're okay with it,
Embrace the suck.
right? So when you're coding, you're gonna go through these like kind of this emotional roller coaster. Just roll with it. The biggest thing that's gonna get you in trouble. I'm scared, I'm gonna take a day away from it. Guess what? It's still there, it's still scary the next day. Then you're like, I'm really scared, I'll give it 2 days. Then now you're negotiating, right? I'm gonna work my ass off the next 2 days. I'll push it off one more day. And then suddenly you had 3 days of runway you lost. You'll never get it back. So when we say in management, you have 3 choices: quality, time, and money. Choose 2. So if you want something done fast, it's going to cost you a lot of money, or you're going to lose quality, but you're not going to get both, right? The problem here is what I found is the most restrictive thing is time. I wish I could have a time machine, right? I was actually our company was late on one project and I was slated to create a time machine. That was my goal when I put on the board. And so every week they go, where are you at with your task? And I said, well, if I'm making a time machine, as long as I get it done the day before I die, we'll be on time. So I procrastinated. So still to this day, my old company will make a lot of money later. All right, so what I want to do today is today is where we start doing optimization. This is where it gets really cool. But I want to kind of knock down some people's fears of PA1, right? So very quiet, it's still too quiet. I know from the office hours, there's a lot of confusion, a lot of problem, a lot of stress. So the first thing is, what problems are you having? Let's see if I can go through a couple of these here. We'll do the lecture. And then we'll go back to like kind of question and answer thing, right? So what questions or problems people are having with PA1?
I can start off because I just got this figured out from Marcello because he is fantastic with this. I realized that it was for the big 4. I had accidentally duplicated a constructor in the H file, and that caused an entire test to crash.
Right? So everything that you do in your H file is prototype and data. That's it.
Mhm.
Anything that you do code, you do in a CPP file.
Right.
So it's got to keep that straight all the time.
Mhm. Yeah, that was the one issue I was coming across, and it was causing I'm terrified to do this, I'm gonna wait a day. I tried to look at this for another day, I couldn't figure it out. And it was just that, and then I looked at one little line. It's like, oh, hey, yeah, just delete this one line, you're good.
And sometimes what I say in my architecture courses, and trust me, this class is 0 work compared to my architecture classes. Because everybody in architecture class already made it through this class.
Mhm.
That's the prereq,
Okay.
right? And I was telling them this one phrase: don't get married to your code. work on the code, we stress on it, we get it working. And then we're like, just good to get this one part in there, then everything will work.
Yeah.
And because we're bullheaded, we're stubborn, we're trying to build on a bad pre-solution or bad previous code.
Mhm.
And sometimes the best solution is, all right, let's start again. Because you gained experience, you just don't know it yet. You gained a lot of experience in that first approach. Sometimes it's better to stop, redo it again.
Right.
And then if you did, you would not have done that cut and paste problem.
Yep.
And it would have been working.
Yep.
Right. So sometimes it's good to restart.
Mhm.
The big thing here is don't get emotionally attached to your code. Right. It's I watched an interview a long time ago with Tiger Woods, and his dad was trying to teach him, like, okay, you're putting, and the putt is for $500,000. You make the putt, you get 500,000. If you don't get 500,000. Where's your head? And he told it was really interesting. He goes, that's not my 500,000.
Mhm.
It's not like, oh my God, I'm gonna lose 500,000. You never had it.
Right.
Look in your pocket, it's not there. You only get it when you have it,
Mhm.
right? So this code, it's not your code, right? Don't get emotionally attached. Now, it's really interesting, when I was coding in industry, we would code machine code.
Mhm.
So what you spent time doing PA1 would have taken a month to do in machine code.
Right.
And then you get so far and like going, yeah, it's not fun, delete. Right? You're like, there's a month worth of work. You just hit delete on, right? And you kind of get over it. So don't be afraid to throw away your code.
Okay.
Right? And even if you fail getting the problem to this point, you actually gain a lot of experience to get to this point.
Mhm.
And it's real experience. 1,000 know to know what not to do. So when I learned how to ski, I used to actually compete doing downhill skiing.
Mhm.
And I was self-taught. And what I would do is right before I wipe out, don't do that again.
Right.
And eventually I started skiing and I started beating people and started racing and all this sort of stuff. And all I did is right before, when I did a mistake, I'm like, don't do that again. Did I know how to ski? No. I just knew what not to do.
Right.
And what was left was how to ski. So if you make a mistake and you can't get something working, then you kind of got, well, don't do it that way. And there's one less option.
Mhm.
So my mode is, you're gonna make mistakes coding, that's normal. Code is always right.
Mhm.
You just don't understand what it's doing,
Mhm.
right? But don't make the same mistake twice.
Mhm.
That's really as long as you don't make a mistake twice, you're still going up the hill. Might be going up it slowly, but you're going up the hill. Right?
Mhm.
So what problems are people having with PA1?
I have like little odds and ends, like I have the core of my code written and I think it's right, but there's errors getting thrown. Like only 4 or 5 of them, and I'm trying to hunt them down and figure out what the heck it's.
Okay, so let's go through some of the basics on PA1. So we have an order. And that order owns hot dogs. All right, so these are hot dogs. And what I mean by own is they're responsible for them. So you can think about it as like order now owns and controls. Pretend those were 3 dogs or 3 cats. And you were their order. You're the owner of these animals. You're responsible for everything about the animal, feeding the animal, doing the stuff. And sadly, you're also responsible for destroying the animal, right? In a humane way.
Sounds so bad.
Well, when you have animals long enough, you'll know that what I'm saying is absolutely true. All right. So a hint on ownership. Everywhere you see a new, somewhere in the code, it might not even be in that file, it might be in 3 files later, there'll be a corresponding delete. So there has to be 1-to-1 on this. If there's 100 news, somewhere there's 100 deletes. And if it's a mismatch, you're leaking. Right? So the hot dogs, you'll see is that I will do this, I'll do hot dog. Right, and then somewhere over here, I'll do order. And I'll say, you know, P Jamie. Add hot dog. Oh, I'm sorry. Add P. So what we're gonna see is, here's a new, here's the pointer to it. And then when we add it, guess what? Jamie now owns it. So in Jamie's destructor, it has to delete the hot dogs. Now, how does it do it? It's going to sit there and walk a linked list, start at the top and say delete, then delete, then delete. Right? So we have a stand. The stand has, let's say, 2 orders. Each order has, this one here has 3 hot dogs. And this one has 2 hot dogs. Okay. So the stand owns the orders. The stand does not know hot dogs exist. If you look in the stand data, there's no word hot dog in it. Right? So what does the stand do? Stand goes, okay, I'm going to start at the first guy called delete Jamie. That's it. Then Jamie is going to delete the hot dogs. Right? So then Jamie is going to go through this and is like, okay, boom, and deletes the hot dogs. Then the stand will go, Sansa, delete. And Sansa goes, boom, and deletes the hot dogs. So you're delegating it. And that's the key. Don't try to outgeek it more than that. So what's nice about OO is that it's kick the can. Not my problem, it's yours. Tag your it. The next I like, I'll try to do as little work as I can, give it to somebody else. So Stan just says, hey, I just had to delete an order. Then the order says, all I have to do is delete a hot dog. Then the hot dog goes, I have to delete.
Week 2.
Cool.
Slowly getting
Why is-
into the
why is
swing of
this-
things.
My email just opened up and turned the volume up. Okay.
Just give your credit card over. And be set. And the hot dog then deletes. In this case here, the hot dog is nothing because it doesn't own anything. It just has simple data. Right? So that's the first thing. Do not overgeek this. One level, one level, one level. So I'm gonna give you a pseudocode for the delete for stand. It should be something like this. While. When you walk in linked list, it's always while. Go to next order. So I'm not going to give it to you, but it's pretty damn close, right? The order. Go to next hot dog. So you can see, this is the gist. Stan only worries about the order. Hot dog, the order only worries about the hot dog. And that's gonna be a big part of the problem, is the deletion. The next thing is deep copies and deep assignment operators, right? So if so we have an order here, Jamie, right? We can do one of two things with Jamie. We can copy it. So let's just say Sansa wants exactly what Jamie's ordered, right? So here's Sansa's order. Now, Jamie has 3 hot dogs. Sansa needs 3 hot dogs. Do not point to that hot dog. Now, Jamie and Sansa both are fighting over the same damn hot dog. Unless you want to see some kind of Lady and the Tramp where they both eat the spaghetti together. We don't want that, right? Especially because they're siblings, right? No, I guess they're not. Never mind. So what we do is we create 3 new hot dogs. X, Y, Z. It's going to be linked together. Remember, I'm worried about on this assignment is correctness, not speed. Then you take the condiments and copy it over to here. Condiments over here. And that's your deep copy. Deep copy meaning you copied stuff from the high level over, right? And then deep, you're going with what it owns. Does that make sense? Was this covered in data structures? Deep copies?
I don't think it was.
No, it was not.
If not, shoot me a private email, and then I will beat up on whoever didn't teach you. If they're at the Paul.
Yeah.
It'd be quite audacious to go yell at somebody in our school. I've been known to do that, so don't tempt me. All right. So this is a copy constructor. Assignment, right? I was looking at the code here and I'm like going, oh, I could have made the unit test even more evil. And I'm regretting this. So the fall, they're gonna get theirs. You are, here's Jamie. And it had, I should have just left this page. Has 3 hot dogs. Right, and here's Sansa. Sansa right now owns two hot dogs. Okay. And you do something like this. Sansa equals Jamie order, right? So it's an assignment. Here's what you do, and then I recast this one wrong, and I don't think I put in the unit test. Sansa needs to get rid of her hot dogs. So she has to go through there and go, boom, boom. Now you're free. Now she creates 3 hot dogs, links them together, and then copies the condiments over. why did I delete those two when I could have just added one more hot dog, right? And just rewrote the condiments.
You'd have a memory leak with the 2 hot dogs you didn't delete.
No, I own them. Sansa owns them.
I mean, if you hadn't done what you just did, you would have had a, if you just like reassigned a new head of the list.
No, if I just changed the condiments, like, let's say Jamie's only had mustard and I just replaced Sansa's ingredients with just mustard. It would look like the same hot dog.
It takes more time. You have to delete, well, you have to,
I'm not worried about speed.
Is it because the assignment operator wants to point to the other?
You
Hot
gotta
dogs?
separate these. These hot dogs were an instant in time Sansa's.
Right,
You're saying copy these, throw those in the garbage. Because somewhere else in the code base, there might be a pointer to the old hot dog. And now it'll be pointing to the new hot dog. And now suddenly you've got a cross wiring issue.
right.
So you always, as good a citizen, get rid of what you own, throw it in the garbage, start again. I did not test that, so
I thought there was that in there. Oh, I guess I kind of just did that anyway.
I will test that though. So that's, those are the things. So this deep copying and deep assignments are almost the same. But if an assignment, because you might have owned something previously, make sure you throw it away before you do the assignment. Right? So it's kind of like this. Think about this. You're a medieval knight and you have a sword and you're gonna assign Jamie's sword. You have one hand. You drop your sword and you grab that other sword. You don't take your sword, it's like going, God, I got 80% of the metal, let's reforge it and straighten it out, make it look like Jamie's. Right? We're gonna just drop it and grab the new one. Right. All right, bitwise. You guys, I'm gonna show you how to do bitwise manipulations, and I'm not kidding. This is painfully easy. It's like embarrassingly easy. What the hell, right? So we have bits, right? 1, 0, 1, 1. What if I want to set that bit? I just OR it. And boom, it's set. So OR, this is engineering terms, but let's just say OR. Right? I want to clear a bit. Let's say I want to clear this bit. What do? I create what bit I want. Here's my bit pattern. That's the bit I want to clear, right? One's complement. Dunk. And them together. Now you see that bit is cleared. Your enumeration has a bit. All you do is take your enumeration, cast it to an unsigned int. Now you got the data. You want to mask? Tilde. Whoop, now it's masked. And you just cleared it. Take that mask, take that bit pattern, just OR it, it's set. That's it, nothing more than that. Now, if I set this bit 10 more times, right? It's still, oops. I'm setting this bit 10 more times, yeah. It still is the same. I can OR it. Once I set the bit, I'm still setting it. It's not going to change signs. Once I clear it, I can clear it 10 times. Still is cleared. Right? No mustard. No mustard. No mustard. Okay, I gotcha. No mustard. Shut up. Add ketchup. Add ketchup. I got you. I got it on my sheet. I'm adding ketchup. Shut up. Right? That's it. So bitwise set. Bitwise OR with value. Bitwise clear. Mask. This is the ones complement. Bitwise and. That's it. Nothing too stressful. And if you want to like, you're into this, there's this whole book called Hacker's Delight that I put a link there and I kind of highlighted. Holy cow. It's 400 or 500 pages of just tricks. Like how many bits are in this data? What's the largest power of 2 I can get from this number? What's the I mean, just left and right. Does this thing grow right, grow left? Does it stack grow up and down? It has all these different patterns on it. But bit set and bit clear. I know they went over that, you know, systems. All right. So next problem. I got time 15 minutes, I'll box it to do a code review or something of somebody's code, like give you feedback on your code. Anybody wants to do this? This is a code review. Sure.
I mean, you can use mine, but I'm done with the project.
Yeah, that's fine.
Okay, go for it.
I won't show everything. I'll just do like one function.
Yeah, please. I'm desperately trying to figure out how to actually like structure my code so it's supposed to be the right way.
So here's the catch. For code reviews, and I've done these professionally, so you give lectures at other places on how to do code reviews. It's really simple. How you do a code review is you use the rules to Fight Club. Right? And so every time you see the word Fight Club, you replace it with the word code review. And also the rules make complete sense. Right? So code review rules.
Gentlemen, welcome to Fight Club.
Code review.
The first rule of Fight Club is
Code review
we
is
do not talk about Fight Club.
code review.
Second rule of Fight Club is you do not talk about Fight Club. Third rule of Fight Club, someone yells stop, goes limp, taps out. The fight is
Code
over.
review is over.
Fourth rule, only 2 guys to a fight. Fifth rule, 1 fight at a time, fellas. Sixth rule, no shirts, no
We're gonna
shoes.
make that one looser.
Seventh rule, fights will go on as long as they have to. And the 8th and final rule, if this is your first night at Fight Club, you have to fight.
Let's see. All joking aside, that's not actually bad rules for code review. You know, what is in the room stays in the room.
Yeah.
You know, it will go as long as they have to, right? One fight at a time. I mean, this is kind of good rules, right? All right, so I had one volunteer or victim. Help me.
I did M Delga 49.
There you go.
I did public humiliation math classes at college. I'm familiar with
All right,
it.
you're well versed in this monster.
Oh yeah, it was great.
Yeah, well, this isn't bad. It's just, I'm gonna get, so the problem with code review is I can give you PAs, I can say this is correct or wrong, but I'm not gonna give you quality. Like, you did it right, but there's 3 other ways to do it. I like this way, and here's why I like this way. And eventually you start seeing things, right? So, and we'll try to do this more. Oh, good God. You can see we have a lot of students. All right. I try to do this. I want to try to do this more frequently because I think you guys get a secondary lesson, you know, doing this. All right, I'm going to pick on. I'm going to pick on.
For the record, I would have failed that test you described, and I'm gonna go on the board.
That's fine. I'm going to pick on hot dog. Constructor. Which you don't have. Oh, here it is.
definitely finished.
I thought constructor.
I finished it.
I finished it live. Haha, you caught me.
I thought constructor. All right. What's the first thing that jumps to your head? That's missing.
The condiment setting to the the unend a whatever the first plane, right? Was that the first thing in the enumerated list?
The condiments right here is under here, condiments.
I just know it stands for like unsigned integer.
Right.
it's-
Oh, you're seeing like just literally use an enumeration. Okay, cool.
I put them in the wrong
That's
order.
not the first thing that jumped out at me.
I put them in the wrong order.
Okay, we'll get into that.
You talked about at the beginning of the office hours, you can do the initialization. Wait, no, not the initialization. You can set it to default since you're setting everything to 0. So
Right, so
better.
if everything's 0, you can get away with a freebie. So default is everything set to 0, right? So this is obviously 0. Now, if I was evil, I'd make plain some other weird number just to jack you, and now you can't do that trick, right? And null is 0, it's effectively 0. So these are all 0, so we could just say conch and hot dog. Right, boom, that still works. Okay. Let's go back to hot dog. Next one. All right, first thing that jumps in my mind, this. Use this everywhere. This arrow indicates ownership, right? So we would always do this arrow. That says now these variables are variables that are inside the class, right? Next thing, you're copying over the condiment, right? This is a copy constructor done correctly, but HD, right? So this is your copy constructor. Now, I tend to, this is just me, I tend to use the word R, saying it's a reference. So I use P in front of things for pointers and R in front of things for references, just to hit me over the head. Now, if you take this to the extreme, you have Microsoft, which is called reverse Polish notation. They'll say pointer to a 0 terminated character, PSZC. Right? So then the name of the variable, like, whoa. So I don't go that far. I just say P and R, kind of good. So RD, right? So this, I'm just showing you how I would do this. Second thing, there's no other R's or in the variable here, so I'll sometimes just truncate it just a flat out R, right? It's the only one I'm talking about, the only one I have. Get condiments. Get condiments is a public door, right? We can do get condiments. We're inside the class. We're inside the class. So as a member of the class, I have access to all the variables. So why should I go through a function to get the condiments when I could just say, here's the condiments directly? So I would go R condiments. Next thing. This is a constructor, right? All constructors have an initializer list. So here's your initializer list. It's the little colon here. If you don't define it, it defines one for you. So let me show you what the initializer list is doing. It's going comments 0 max no where so oops. He didn't specify this, so this is secret, but this is happening. So what's happening here? Let's pretend I'm a condiment variable. I get rid of 0. Then I turn around on line 35, I get written with another value. I got written twice. Right? So we had a thread going in Piazza saying, what's the purpose of initializer list? Why is it faster? Because if I just did this inside the initializer list, now I don't even have to do any of that. And I touch the variable once. So now it's technically twice as fast. Instead of me running 6 variables, I only wrote 3. Right? The second thing that's cool about this is the arguments here are going to be constructed in the order that they're laid out in memory. So you notice I went back here and I cut and paste this, right? Into here so I can see the ordering. That's the order it will do. Condiments first, next, and previous. If I put next in front of this, I have to change the ordering over here. So the ordering of the initializer list has no bearing on the order they're executed. They're always executed in the order they're laid out in memory. So it's good to just keep them matching. So if they're laid out ABC, initialize it ABC. Now, there's another advantage of an initializer list. I don't believe in exceptions. It's not, I didn't go to that religion. A lot of people have exceptions. They teach you it, and I'm sorry. I apologize for the rest of the community. I think they're wrong. Exceptions. What happens when an exception happens?
Program stops usually.
Stops.
You get a system call, you handle, you pass it back to the kernel and be like,
Yeah.
stop.
Have you ever seen somebody do it successfully?
What do you mean?
Do exception successfully. So what happens is it doesn't work. Goes up a level in the call stack. That call stack doesn't deal with it. Goes up a level in call stack. That call stack doesn't deal with it. All right, you still have a problem. You got bad data. What do you do now? Print a cute message. It crashed because pointer was null or divide by 0. And then what happens? You reboot the machine, you restart the program. Think about it for a second. 90% of the time, 99% of the time, oh shit, something bad happened, reboot. Right? What you really want to do is sit there and say, the only time I've seen exceptions kind of used correctly, and I'll still say kind of, is on network traffic. They go, oh, a bad packet comes in there. I don't know what it is. Screw you, goodbye. We'll just ignore it, right? So they use exceptions for that. Or you can just check it. I got my packet in there, doesn't work, put a dummy packet or skip it. You don't need the word exception for that, it'll try and catch. But a try and catch will roll through the stack until it gets solved or crashes, right? So if you're constructing a hot dog and in this initializer list, there is an exception. It will finish the initializer list before it throws the exception. Very, very subtle problem. But if you had, it was initializing 5 variables and one throws an exception, it will still initialize the other 4 variables, then throw the exception. So initializer list will guarantee to complete in the view of an exception, right? But the reason why I like it, it's faster. Right? You can still do stuff in here, and you do stuff in here that kind of is ugly. Looping through things, doing something kind of weird and crazy. If you need to do a dynamic allocation, you do an initializer list still. You can still call new inside of there. Let's say we want to initialize next to hot dog. Don't ask me why, but let's just pretend we did. You can just go new hot dog. Find the key at some point. Oh. Hot dog. So you can still do that if you need to dynamically allocate a pointer and initialize our list. But initializing the list is just faster. Right? And then the other thing I would do here is, just because I'm a crazy guy, I can go P next. And then P previous. Just to hit me over the head as pointers. Right? And that's pretty much the time I'm allocating for review. We'll go deeper, and every week we'll go a little bit more and give you a little more nuances there. Weird things like you'll see me do sometimes is this. If X equals 5, right? I don't write that. I would write it, because what if you forgot an equal? Right? It's still valid. So I will do it this way. Technically the same. But if I skip an equal, you can't assign X to a 5. It's an illegal left-handed variable. Right? Every time I see a conditional, even though it's guaranteed to execute this line of code, right? I put parentheses around it. The reason why I put parentheses is if you later wanted to add a line of code, you know that you're tying it to the conditional or you're tying it outside the conditional. What happens is, and this is a big problem that's starting to come out now, a lot of people have done Java. Sorry, there's a lot of therapy ahead for you. So you do this, like, oh, Java, you could just indent it, and this will work. Then you'd sit there like, oh, I'm doing my new statement, and I'm thinking that the www will be bound to that conditional. No, www will always be executed because it has no conditional, no nomenclature around it. So always put the parenthesis around it. If you do if, else if, whatever, always put an else at the end of it. That's the last condition. If you do nothing, I just put a comment there and say do nothing. Which means I thought about the options and my choice is to do nothing. You know, so we'll get through this stuff, but overall, good job. Trust me, I'm generally meaner. So that means your code wasn't that bad. But you'll see that over time, I'll start tweaking you. Now, these lessons, it's a religion. So, you know, I'll get another senior guy here and I'll say, oh, no, don't do it that way. You know, don't use P. Oh, who would ever use the word P in front of a pointer variable? That's just crazy. So you'll get different opinions. And what will happen is when you work in industry, generally you tend to kind of follow the style that your team is doing. If you're working on projects like I did, where I worked with projects with multiple companies, multiple countries, you mimic what's around you. So if they're using the curly brace indentation, this style, you follow that in style, because you don't want your code to look so different than everybody else's. There's also programs that are really cool. When you download your code from version control, you sit boom and reformats it to your style. Then you hit boom, it reformats it and puts it back into their style. I love that because then you can have your own look and feel and you can give it back to their crazy one. Right. All right, like I said, if we have time later, we'll go through this. We'll go through some more stuff. Is this helpful at all? All right. All right. So let me go through the basics this week. I'll just go through that really quickly. The basics this week is really simple. Technically, it's easier than what you just did. It's inheritance. So it's just, but I'm going to also have you try in Java, in C#, they only have public. We also have protected and private. So the first we use this stuff. So here's the code, the basics. And you have 5 tests, really simple. And all you're going to do is just follow the things. Problem 1, work on A.H. So A.H says class A is gonna leak memory, modify class A, do not change class B. Prevent it from leaking memory. So here's class A, pretty straightforward, right? And then here's A code, right? Here's B. Oh, I have down here a diagram. So here's a little diagram. And this is one of the reasons why we're using Enterprise. You get all these diagrams kind of out of there. So here's A and B just derives from it. And on B, here's B. It has data and a pointer, and then B has a new. And if you look at the test, I create B, I cast it, and I check the value. I create B, it's A. This is called compile time polymorphism, where I take a derived class. So let's imagine my base class is a dog, an animal. My derived class is a dog. I said, okay, and this line right here, I say, create a dog, say it's equal to an animal pointer, which is legal. Then I say delete the animal. And when I do that, it leaks memory. So you're gonna have to change the class A to make sure it doesn't leak. So it's little questions like this. And there's another one that's goes into more and more kind of, casting operators and stuff like that. So this gets pretty good. The hard one here is towards the end, we have diamond pattern. This is a huge no-no. Java, from first day they made Java, they said, no multiple inheritance, bad. But multiple inheritance is in C++, it's used, I use it. I use a certain rule to make sure I don't get into trouble, which I just keep all my names separate. So where multiple inheritance gets you in trouble is if G has a variable, a function called foo, and F has a function called foo, and H you call foo, which foo do you get?
No.
That's why diamond pattern is dangerous. Now, if you use diamond pattern, you sit there and say, everything in G is called G foo, and everything in H is called H foo. When you're down, I'm sorry, F, everything in F is called F foo. Then when you're in H, you know which one you're calling, right? So it's pretty simple. So the problem with the diamond pattern or multiple inheritance is if you don't give the names smartly, you can get name collisions, which causes confusion. So there's an exercise on this. There's an exercise on virtual inheritance. But this is the one that's interesting. You're given a class here. And this is, let's pretend your company buys software from company X. Like, here's this program, and here's the interface. And you look at the interface, you're the architect, you're going, holy cow, this is horribly written. I don't want to give it to my team because my team will use it incorrectly and break everything. So you sit there and say, I'll wrap it. Let's put a big box around it and just give a couple of functions. So here's the horrible interface, everything. And then the wrap, you just drive it privately. But then you expose what you want to expose. So you can expose part of the program, certain variables, you can make certain variables stay private, you can make certain variables public. So private inheritance, a lot of people don't know how to use it. It basically says, I derive from a class and everything is private. The functions, the methods, everything's private. And then it's up to you to expose what you want to be public or protected or private. You get control of it. So you would write that. And for this assignment, you're going to compile it in debug, and you'll just run this here. You get your unit tests here, and everything will work. And then you're going to turn around, compile it again on this wrapper solution. And this wrapper solution is, I'm looking for errors. So I'm going to count how many errors And I'm telling you which errors I'm gonna get. I'm not hiding anything from you. It's right here on the private adherence. It's going to check down here. These should all generate errors. And if you wrapped it correctly, it goes boop, 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 boop. All these are errors. And if I count the right number of errors and the right number, you got the point for that one. So I just want to mention this because a lot of times I forget, and then also we're out of class time, like, oh shit, I didn't talk about basics too. All right. So now we go into the coolest lecture ever. All right, data alignment, data padding, right? And what's cool about this is everything we talk about in data alignment, data padding is true for C#, is true for Java. So what I say here will make your Java code go faster, right? I always give a calendar date. I didn't update this one, but this is the calendar date in Mayan long count. Here's what each of the terms mean. It goes 2018, 2020, 2020 is repetition. Mayan is squares. Aztec is circular. A lot of people, and I'm very offended, they say this is a Mayan calendar. It's an Aztec calendar. And if you ever get a chance to go to the History Museum in Mexico City, and if you go there, you have to go there. It's the biggest museum I've ever been in. That circle dial is like 12 feet tall. It's absolutely huge and gorgeous, right? But here's Mayan calendar squares, just in case you're wondering. All right, we're gonna go through data alignment and data size. We're on a 32-bit processor. So that means characters are 1 byte, Booleans are 1 byte, ints are 4, floats are 4, pointers are 4 because it's 32 bits. Doubles are 8, right? But remember, people can adjust the settings on their compiler. So this is historically what it is, and it's kind of what's agreed on. But you can like hop onto an ARM processor running on a microchip or a PIC or something like that. And also all the sizes are different. So you always have to check it. Right. All right. Enums are compiler dependent. Right. So remember that game? Oh, I need a pen. This happened to me before. I don't want to be in hell. If I don't get writing on this. All right, this is where the students help me out. I know there's a stupid button.
Annotate.
Where did you see
That's
that?
for Zoom.
Trying to work though.
True.
Well, there's one for
Zoom.
There is for
Yeah, you can just use the same one.
PowerPoint. Is there a special way you have to set it up? I can't remember.
no this what's it called? Something about the Paul has this thing defaulted in a backwards way. Of course. What's it? It has to be around slideshow. Bastard. All right, I guess we'll go to phase 2. No, there's one here.
like it's
All right, how do you do the annotate? It's on, it's in Zoom.
It's on the, right next to the
Yeah,
pause
right,
button.
pause.
Annotate.
it's
that's what-
expired pause, yeah.
Okay. Oh, this is a stupid thing. All right.
Hopefully the pen can work with that.
Yeah.
Yeah.
Better enough. No.
Oh, boy. Right.
Yeah, erasing over Zoom annotation is absolutely terrible.
You have to like set everything.
All right. Oh, bastard. All right. How do you advance this slide?
You need to change it back to.
We'll hit the right arrow
Yeah.
maybe. Oh,
Oh. All right, that's not gonna work. All right, back to option, real option. Where's the button that does this?
It's gonna fall in.
I don't know if you can get rid of this that easily.
What?
Is it on your like, is it
I
just part on
don't
your
see-
desktop?
what is it gonna be free?
I think you just wrote this on your desktop, not on the,
You did.
Mhm.
Same thing. You were on the Zoom. call.
Yeah, it's it overlay.
Did I do something wrong?
You have to go to annotate on the Zoom call and clear.
Yeah,
Yeah,
cause
oh,
it'll just fall.
yeah, you
in.
got scribbles everywhere.
Yeah,
Oh, trash. Oh.
there's an eraser right in the middle.
They're all drawing.
No, there's a, it's a menu.
Oh, it doesn't, there's no down arrow. How would you know
No,
it's a
it-
menu?
I know. You hover over clear.
That's such bad design.
This is awesome. All right, all right.
Guys, don't do this.
That is such bad design.
This is what we don't do.
Don't make
Making a sign
Alright.
menu that's not. Apparent.
No, it's,
I don't know
it's,
what's going
Oh,
on.
I see.
Yeah, it's
That's
just,
part of the Zoom.
yeah, it's like floaters in your eyeball.
So clear,
Right?
I think you just hover, you have to hover over clear and wait a bit.
No.
yeah.
Hover over.
You have to, the trash can's a menu, not a button. It's
Yeah,
not clear all
Clear.
at once.
we can't quite see what you're doing. I think it hides it. There we go.
Okay, boys.
Yay. All right, that's like really bad interface. So if you guys work there, change it. All right, next thing is, this was working before, so why? Last week it worked. Ah, you bastard.
Worst case, you can like print a PDF of the PowerPoint onto your note-taking app, and then you can just,
No, you'll like this one, ready?
oh no.
This is the.
I know this one works. Wait, let me make sure. Works.
Ah.
All right, so this is combat approach right here. We're just gonna nuke everything here, and copy another one into it. All right,
Okay.
and now
You don't see it.
we'll open the other one.
Yeah, that's really.
And I know there's a setting that I'm missing.
Is there a little setting with link to the slides?
Now go back to,
Turns out the slides are right protected.
Right.
Oh.
Oh,
yeah.
no, it's not good. That's just because I've been in this shitter before. All right. All right, so, enum. Color. Red. Blue. Yellow. Black. What's the value of black?
Everything. Or nothing.
Isn't it the absence of everything? Like, all of it?
So these zero.
What's the value of black? It's one. It just one, whatever the one before it, it's +1, right? What's the size of color? If I'm gonna use color in a structure. What is the size of it? How many bytes?
That's a question, not an answer. Is it Cause I tried to do this on something else and it's like, isn't it like the length of your largest number, like the size of your largest number, how many bits you need for that?
That's the minimum. You're close. That's the floor. Right? So, I went like this right here. Enums are compiler dependent. So yes, it depends on the compiler. Right? So the biggest number here is 4. I mean, 0. This is 1, 2, 3. So we can get away with 1 byte.
Oh, 2 bits.
So this could be 1 byte, 2 byte, or 4 bytes up to the size of an int. If you set this equal to, you can change a flag in your compiler saying treat enumerations as ints, then this will always be 4 bytes. Right? But Microsoft does a trick. They will add a word here called dword color. And they'll say equal to 0x7ff. It has to span the range. Because this number is so big, it forces it to always be 4 bytes. Right? Now, you can do this. You int, 32, and now this will declare the size of it as well. So a couple different ways, but enums are kind of problematic. Right. Leave that side. All right, so there's this function called size of. The size of function tells you what's the size of the variable or the structure. And with padding, so it's the total size, total number of bytes. Size of is a magical function. First of all, just make sure we're clear. I use structures and classes. I use those words interchangeably. What's the difference between a class and a structure?
Doesn't have to do with what's private and public, like one of them has, I think class has public and private and structure is just public. Or,
It's what it's defaulted as.
yeah,
Class is defaulted as private. Structure is defaulted as public. But I can put the word public and private in a structure or class.
change it.
So because I always put public or private in there, I use the word struct interchangeably. Yes,
Can you put methods in a struct?
yes,
Oh, okay.
constructors, big 4 operators, everything's the same, except this is born private, this is born public.
I just, because in C, like, I think of a
No,
C struct. and-
C# is different.
I meant C, I've never used C sharp, I meant C, like C.
So C never
Wow.
had structures, I never had methods.
Right.
Yeah. Right, so if you see me using the word struct or class, they're the same. One is born public, one is born private. If I want to make my structure class behave like a class, I just write the word private as the first line. Now it's exactly the same. If I want my class to look like a structure, I just make my first line public. Now it's the same as a struct. That's all. It's only difference. So you have methods, you have constructors, you have data, all this other stuff. All right, so the size of, will calculate the size of a structure, all the variables, and all the padding. It tells you the total size. Right? So what's the size of this? Well, characters are 1 byte, character 1 byte, and character 1 byte. So people who haven't seen this slide before, what's the size of the structure? Total size.
Would it be like 4 bytes or something?
Someone says 4. I count 3 variables, but yeah, you got 4 somehow.
Alignment, I think, is what the reason.
Yes, see,
Isn't there
what I'm gonna do is demystify alignment, right?
Isn't
This is
there like
actually
a-
3.
Okay.
3 floats, I have 3 bytes, 3 of these, right?
Ah,
What's the size of this one? In integer and integer. Integer is 4 bytes,
8 then.
right? So it's 8, cool. Right, easy enough. Integer and a character. What's the size of this structure? We have an 8, we have a what?
I'm gonna say 5.
The 5. Right, all right, so turns out it's 8 and not 5. And the next 4 or 5 slides is just to argue and articulate why. right? So it's kind of like, it's really easy, like, when you're looking at the slide, like, why the hell are we doing this? I'm like, to tell you why it is 8, right? Whoa. That must have been the cut and paste there. All right, so here is n byte aligned address. A memory is said to be n byte aligned when n is the power of 2 and the address is multiple of n bytes, right? Easy peasy, right? Here's how I look at it. Write the address in binary and count how many zeros at the end. 2 to that power is how many bytes it is aligned. Right? So what's the alignment of this? You write the last, you write the end of this in binary. So here's F4, and we count from the end. We always start from the edge. We count how many bytes, how many zeros. So we start here, we're like, I count 1, I count 2, 2 zeros. So it's 2 to the 2, so it's 4 byte align. Right? So let's do another one. F8. Right? F8, we see 3 zeros at the end. So it's 2 to the 3, so it's 8 byte line, right? 2 to the 3 is 8, right? But let's pretend we're bad at counting, right? So you start from this edge. I count 2. Okay. I count 1. Okay. I count 0. I kept my eyes closed. So this address is 8 byte align. It's also 4 byte align. It's also 2 byte align. It's also 1 byte align. Right? 8 is the maximum alignment. Right? So when we see someone that says it's 64 byte align, we know by definition it's also 32. It's also 16, it's also 8, it's also 4, also 2, also 1. Right? So we just count the number of zeros at the end. So this one, C, 0, we count 6, so it's 64 byte line. That's the maximum. So what it turns out, the compiler is really fast is if you put your variable types on aligned address boundaries. So if you keep all your characters out on 1 byte on boundary, it runs fast. If you put integers that are 4 bytes, put on 4 byte address boundaries, it runs fast. If it's a double, put on an 8 byte boundary, it runs fast. So we like this. This is aligned data. You can put your compiler in misaligned data, which means you have an 8 byte double, but it's on a 1 byte boundary. So then you have to read and nibble, shift it over, read and nibble, shift it over, or them together, put it together. Oh, by the way, here's your data. Sorry, normally it takes 1 cycle to read, but it took 20 cycles to shuffle around and do this. We do that on routers. We do that in printers. Because your printer is like, what's the smallest amount of data that we send over to the HP printer to print? So it makes it unaligned. Then the compiler just starts chopping apart, moving stuff around and gives you the data. But for speed, we like alignment. Yeah, I just talked about that. All right, so here we go. Here's our data layout. Let's assume the first address is 0 with 1,000 zeros, so it's infinitely aligned. And we're going to write X as an integer. So we write X0, 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 X0 for the first 4. Then the next address byte is address 4, 8. So let's look at this. X is on a 4 byte boundary. It's on a perfect boundary, right? That's cool. B is on a 4, address 4, right? Address 4 is 1, 0, 0, right? So there's 2, so it's 2 to the 4. I'm sorry, 2 to the 2, 2 to the 1, 2 to the 0. So it's a 4 byte, 2 byte, 1 byte. So it's 1 byte aligned as well. So cool. This data works out great. So why is it 8 and not 5? Right? So now let's look at how we might use the structure. in the future, right? What if we take the structure and we create an array of 3 of these? Right? And so we just have the 0, the 1, the 2. Now we're gonna sit there and put in memory. And we're just gonna write down the first 4 are X, the next one is B, the next 4 are X, the next one is B, like this. Now, if we look at it this way, we see X0 is aligned. B0 is aligned, that's cool. Then X1 lands on address 5. X1 is 5, 1, 0, 1, which is 2 to the 0, which is 1 byte line. It's not 4 byte line. So now we're in trouble. So X1 is not aligned, so we're gonna add some padding to make X1 align. So we're just gonna add some dead space there until it aligns. Now we look at this dead space and we get that X2 is aligned. And I mean, X1 and X2 are both now aligned because we added that padding, right? Now, if we look at the size of this, that's your structure, it's 8 bytes. So the reason why it's 8 is that it might, there might be another, it might be used an array and the guy right underneath it has to be aligned. So we have to add the padding for the person below you. So you're happy, the first index works great, X0 works great. But X1 in an array blows up because it's not aligned. So we have to add padding to our box. So this compiler looks at the structure and goes, I don't know how you're using it, but if you use it in an array, you better add some padding. So it adds the padding as a preprocessed phase. Right? So to verify this is really kind of interesting. We use this thing called placement new. Right? And so what we're going to do is we're going to fill up memory with A, and we'll go placement new, is look at the memory. So here's our data. And this is first of all the code I show you in class was real code that I cut and paste. I was a student and I hate books and examples where they give you code and you type it in and like, it doesn't work. So I always write the code, then cut and paste the code into the slide so I know it worked, right? So here's the code. And what I'm doing here is this first line here is create a chunk of memory. Boom, big chunk of memory. Next one, fill it up with A's. You didn't think I was going to fill the whole box up.
Yeah, I was waiting for you to stop at the 8th one.
Oh yeah, the problem is when I go faster, my writing's already sloppy. If you want to see it go to medical level. So I was talking to the doctor, I go to the Mayo Clinic a lot, and I was talking to him like, why are your handwritings bad? He goes, for the last 30 years, we had to write everything down. So you just kind of just scratch stuff. And he goes, surprisingly, pharmacists and other people know your handwriting over time and they know what you meant. Right. All right, so let's fill up with A's. Then we're gonna do placement new. What is placement new? You probably haven't seen this before. It's new. And all it's gonna do is do a constructor at that address. It doesn't create the allocation. So normally new is this. When you see new, dog, what it's gonna do is gonna say, create the space for a dog. So this is a space for a dog. And then it's going to fire off the constructor and it's going to pass in the numbers in the constructor. So it's a malloc followed by a constructor. Placement new says no malloc, just do the constructor. And where do I do the constructor? At the address you give it. So it's going to do the constructor at P. So boom, it does constructor at P. This is a default. right? So that was this line. Now I'm gonna write the numbers over it. Right? So. Right, so. Take a chunk of memory, fill it with A's, fire it off a placement loop, then put the data on top of it. You notice a couple things. One is, this is 90, 80, 70, 60. We look in the memory, it's backwards. Why?
Little Indian.
Little endian, right? Run an Intel processor, little endian, right? So it's backwards. All right, and look, you see the A's there, right? That matches our padding. So our mental model matches our physical model, right? So we have this thing adds 3 bytes at the end for that it might be used in an array, and we got to guarantee alignment for the next X variable. Right. All right, so that's why it happens, right? So let's do more complicated data. What's the alignment of this? I mean, what's the size of this? Sorry. 24. 24, okay, anybody else? Right, so that was a good guess. 24, I mean, good option. And you can see, void is a 4, character is a byte. This 4 now forces some padding behind A. Then it goes character. Now this int forces some padding, and because it's trailing, because remember we can duplicate this whole structure, we have to add some padding after the C, right? So it's 24. Now we look at this structure, whether or not we declare the variables or not, we bought 9 bytes. We bought a truck and we only need enough of space to hold this TV, but we got a much bigger tailgate, right? We bought it. So let's be explicit. We'll put the word pad in there. These two classes are exactly the same size. Now it's like hits you over the head. Hey, there's a lot of extra padding, right? So now, let's rearrange it. Let's take this and move the most restricted to the top and least restricted to the bottom of the structure. Now we have 1 byte of padding, right? We went from 24 to 16. Okay, that means we can put more of these into memory, more of these smaller objects into cache, less data sent over the network, faster, 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 right? All right, so when you take this and reorder these, move the most restricted to the top, and then fill in underneath, right? Add dummy variables. If you have padding, say it out, to describe it out loud, right? Now you're changing the orientation of the data. This could break some bad coders code, right? We're going to break bad coders code. So if somebody just sit there and say dereference p+3 and you rearrange the variables, kablamo, you're reading something you didn't intend. So as long as everybody goes p arrow x or r dot y, you're okay. But if they do some pointer magic +3, this could blow up. Now, I would actually argue if it blows up, that means there was bad coding. We're gonna have another talk with that guy on how to improve his coding. But if you rearrange it, there's a danger, but you should rearrange it, right? So here we go. What's the size of this?
Again.
24, right? I'm going to tell you an easy way to figure it out. What's the biggest one here? size, 8. It's n times 8, has to be. Some n times 8, right? So at least you know you're in the ballpark. Right? And alignment wise, it's really sad. There's a lot of pads right after that stupid character. And then there's trailing pads at the end of it, right? We rework it. Now it's 16. 33% less data. Huge, absolutely huge. Right? So we align data to save space. But we align data because there's special secret instructions that use aligned data. And we'll get to these on week 6. And basically, you can't ever do these really fun functions and programs unless your data is 16 by line. Unless your data is 256 by line. So if your data is aligned, then you can get access to some cool functions, right? There's also DMAs. Probably nobody, did they go over that, what DMAs are? There's little machines in your hardware that will quickly move data from location A to location B. You don't have to worry for the processor. It says, oh, you want me to do this? Thank you. Tell me what address and how much and where do you want to go? I got it. And it's basically it's somebody comes with a U-Haul, grabs all your data, moves it over to another location, and it never touches your processor. It's called DMAs. But DMAs have to be aligned to certain addresses as well. Right? All right. So here's some trends that are really interesting. Processors aren't getting faster. You guys probably, some of you have probably the fastest processors you can buy. If you're somewhere around 4 gigahertz, you're at the fastest you can buy. Theoretically, you can't go faster than 5. It doesn't work. They even taken silicon, had to grow on a space station to try to get better silicon to try to go faster. Didn't work. 5 is the limit. Generally speaking, you're somewhere between 2 and 4 is where you live. So what they do is they don't give you a faster processor, they give you more processors, right? But now what costs the most money? Memory. But really fast memory costs a lot of money. So they try to give you little bit of memory because that costs a lot of cycles. What people don't realize, if this is a processor, i7, right? Want to know how big your CPU is? That's it. Everything else is memory. And it costs a lot more to get fast memory. So you have, and oh, by the way, that's just not one processor, that's 8 processors. You know, it has an 8-core processor there. Everything's memory. Now, if you look at a GPU, it's the reverse. Everything is a processor and very little memory. Okay. So processor getting fast and cache really controls your speed. More than anything, it's your memory, your cache. And so what we got to do is try to keep our code living in cache. So we like our data to be aligned and shrunk because we can put more things in memory, so then our code goes faster. Right? So let's go through caching. Oh, probably time for a bio break. Somebody likes bio breaks here. All right, let's do break.
Enjoy. It's a bio break. Do you have the money?
No, I do not have the money there.
Then no.
Okay, why do I need 120 cores anyway? I don't need that.
It's cool,
but I
well,
don't-
when you take my classes.
Nah, I don't need a Threadripper. I can just like 3 processors together and just run it simultaneously on 3 different PCs.
Yeah, I want to see, take one of my classes and we'll show you the faults of that
I
idea.
don't know. AMD just is absurd with their prices nowadays. 7,000 for
Yeah.
Yeah, I have stuff messed up with my lower spine. I have narrowing between my last vertebrae. And then my butt bone is shifted to the left. Just enough to where it's painful. So like standing, I can feel the tension always.
Mine's the other way around. It's like too much sitting bothers me. I have to get up.
Oh, yeah, I can't sit. If you ever like see me like move around a lot in my seat, it's because I
Yeah.
can't sit.
Yeah,
Like that's purely military. So like I'll shift too, not sitting I'll like shift to one side and then shift. That is purely, I blame military for all that. My feet hurt from that, my knees hurt, my back hurts. All that hurts.
yeah.
There we go.
Yeah.
You done the basic yet?
What?
You done the basic?
Nope.
I don't know if it's basic.
It's probably not that hard.
I imagine people like I just don't want to do any more coding this week. I already have another home assignment. Pretty sure this.
Now it's like, now that I've got the fifth one. And then once that's working, then pretty much the last bit will work. A lot more evening classes than I was expecting.
Yeah, almost all of them right now.
Every classroom is filled. The amount of evening classes that there are right now, it's like every room is filled. It's weird as well. Both my classes that I take in person are in here.
Same room?
Yeah, same room.
Really?
Yeah.
Mine's like right next
I
to
had 3 classes in a row next door,
Okay.
like both of my in-person for, well. never mind.
Okay, my other CS class also in here. It's weird.
So you're doing 347 or?
21.
Oh.
All these numbers memorized.
Oh,
I did all these
I
numbers
look at my DPR very often.
yeah.
memorized. DPR.
The degree progress report. Yeah.
It only changes every 10 weeks though.
Well, yeah, but I plan way far ahead. And because of the way that my degree is set up right now, like all of my open electives are filled because of JST credits and joint service transcript. So like military training, which I'm assuming you had yours go through.
Well, in my grad, I'm in grad student, so
Okay, so it
all
doesn't
my
matter.
stuff was done already.
Got it. At least for leading undergrad, joint service transcript will take military training and
It's a
turn it
big
into
amount.
college credit.
Oh, that's cool.
So I had like 26 credits gets transferred over as college credits.
Specifically electives and like core classes.
It just basically puts it in as like what the training was. I'll have
It
like
depends.
marksmanship training, I have leadership training. I have-
Yeah.
That shows up as a college credit.
I'm guessing all that is
That's
just open
collective.
elective though, right?
Yeah, so literally I could show you it too.
I'm
And
just curious
I
what the
remember last
marksmanship
time I
requirement in
saw
CS
DPR,
looks
it
like.
was
I think there's like a physical requirement or something like elective that counts as that, and then there's like leadership and management, that was like a huge chunk of them that eat up.
That makes sense.
Yeah, for me, I think it was like 45 credits or
But
whatever.
I mean, it's interesting because if you just got to something like business or
Yeah,
entrepreneurship,
that's
it would
what
have
it-
been like, you're done.
Yeah, I did my
Usually great.
master's
Yeah,
in
fun
business
fact.
and I'm done with it, so now I'm back and circle back for.
Computer science,
programming, so
degrees
I
for
already have a
undergrads.
master's in business.
This class isn't
And it
required till the
knocked
last
out
two quarters
almost
of your
everything.
whole.
Makes perfect sense.
Yep, it's the last two quarters.
Yep, I have 1 quarter after this.
Yep, yeah, for game programming in sophomore year.
that is ridiculous.
That's why when I was talking with him about the master's, he's like, go software engineering. Don't go for the master's for CS.
Oh,
He's like, it's, if you're at another school, that would work, but the track at DePaul, they don't tell you what it is before it's too late.
So masters, you go for software engineering?
What if we're already
You
in
gotta focus
CS?
in game systems, real time.
What if you're already there? What's the what if game? For a friend.
I don't know, I'm not good enough to
So,
speak on
like,
that.
This is like what mine looks like at the moment, but open elective is like completely filled.
Change it.
And that's
Oh, they
the,
changed that fast.
What?
and all this training, marksmanship, operation risk assessment, tactical transmission operators. that was great.
Leadership corporal.
Yep.
It takes a good chunk of your stuff.
Yeah, it takes up all my open electives.
And
then for military joint service transcripts, when it goes into my DPR, this is, I can show you, this is what it looks like.
One of my exes in the military, I never mentioned that one.
Yeah, it's like one of the few benefits we get. like,
Yeah,
Oh, no, that's what we're doing, like, I just started mine.
they just care about hours.
And so
So they put it as
everything's
miscellaneous
free.
and it fills up all my open
As long as I
electives.
just go.
Yeah,
you
no,
know what I mean?
that's. Sometimes it's not good. The reason is. Just because you finish all your open electives doesn't mean you have to do You know, take more classes if you can,
Yeah,
but just take more technical courses.
that's,
Always-
yeah.
So like, I think anime is cool, buy a book, take another programming course, that will get you more job, right?
Right.
So always focus on, I always tell my people in my advising is your open electives are just more major electives,
Mhm.
you know, because you need more classes, right?
Yeah, that's kind of how I'm viewing it, where I have that more of an opportunity to take more classes that would actually matter.
Yeah, that's all things you want to be. So are we, I don't know what time, I should have wrote down what time.
I think we started it. Was it 7:15?
I think it was 7:15.
I think it was 7:10. Yeah,
I'm
7:10.
losing track of time.
All right, so we got 4 minutes. 4 minutes.
Before did you go to get the drink?
Oh, after 7-Eleven, across the street.
Not gonna get there and back in 4 minutes.
Hey, man,
The elevator alone is
Hey,
gonna
man.
take 2 of those.
That's
there's
where you
stairs
take
for
the
a
stairs.
reason. and I got my Lamborghinis. I can take those instead.
The elevators here take too long anyway.
yeah, and yet they're redoing the ones at DePaul Center when those are like cheap fast elevators.
Yeah, I literally only take the stairs in this building.
I know, like
I
DePaul
knew
is
you'd get a
literally
kick
like,
out of
they're
that
like, hey, yeah, we're gonna modernize our DePaul, our.
So my friend's a firefighter. And he always tells you when there's a fire in a building, you take the elevator.
Oh, yeah,
What, really?
because it goes.
100%. What is the most bulletproof section of a building?
Yeah.
Oh, because of the.
Right? There's like way less than 1% that the fire's in the elevator shaft. And if it is, it probably wouldn't be working.
Yeah.
When the elevators, when the firemen come to a building, they go to the floor and they hit the key, it just zips the car down to the first floor, so they can take the elevator back up to the fire.
Oh,
Yeah, but if you're in that elevator as they zip it down. what
Then
if
you go
like-
right to the ground floor, like, hi, firemen, you walk out.
Oh, does it not go like insanely fast? It
No,
goes
no,
at,
it just doesn't answer any calls.
oh,
Right.
Huh.
And a sad note is, what do you call everybody who took the elevator at 9/11? Alive, right? So it's a really,
oh yeah, they did. There was a small group that took the elevator. I
Yeah,
remember seeing
so-
that.
yeah, so that's one of those common myths where it's like, yeah, take the stairs. You definitely won't
Yeah,
have
yeah, 'cause it
rubble
were- it
falling
was-
on top of you and stone.
Grab a
like,
whole bunch of old ladies,
no.
got them in the.
so that was from my firefighter friend, and it
Wow.
also makes engineering common sense. Because if you look at a building being built now, especially in the suburbs, you'll see like this big concrete
Yeah.
box that goes up, that's,
Yeah, and then it's like metal
Then everything
framing
else is around.
inside, yeah, it's. I'm not sure about this building, because this building's
this
pretty old.
building actually built pianos. This is a piano manufacturer, that's why you have thick concrete floor.
Right. Did they like cut this building in half or something? Because the one by the parking lot looks so different. Like, it looks like they just bricked up
So this
windows.
building was pianos.
Huh,
Um,
you know.
And so in the back, there's freight elevators wide as grand pianos.
Wow.
That's all I know. And I do know, like, where, when you walk into the turnstiles, there's that research lab, that used to be a McDonald's before my time. All right,
Wow.
all right, caching. All right, so this part here, we're gonna learn about caching. I can spend 2 quarters easily on how caches really work. So I'm gonna arm wave a little bit of this to kind of give you a feel of how cache works. Because the real thing here is cache is real. It does affect performance greatly. But to really understand how it works is insanely hard and complicated. Because the compilers are trying to do things that you didn't know they were trying to do. So when you write to a variable, you write to a variable. Well, it's not real until it goes all the way to memory. But this goes halfway to memory. Then if you read again, it comes back. But if you took a God look at the memory, it doesn't even have that variable in it. So we have write through, write back, look ahead, predictive, flush, all this other type of buffers in cache. It makes it much more complicated. All right. So embedded systems is really a contest, right? What's an embedded system? Your phone. Embedded system means I can't upgrade the processor, I can't upgrade the memory, right? Now, some people's like going, I got a phone that I can change and give myself more RAM. You're giving bulk RAM, you're not getting processor RAM, right? So the key is, how do you make your system better? Is you try to use your system more efficiently, try to get more speed out of it, try to use less memory, right? And this is why I think the video game industry is really into performance. That's where I come from, is that everybody has the same PlayStation. Oh God, we hate those EA bastards, right? So we're gonna make our code faster, or Sony did this. Oh, well, we can do better than Sony. Screw them, right? And so everybody's competitive because they all have the exact same platform. So it's not that your machine is faster, you coded it better, so it gives the illusion you have more things on it. So that's why I think it's very competitive in the game industry for speed, is because they want to give a competitive edge. They have more characters, more particles, more cloud, water effects, you name it. You see this a lot in high frequency trading. Time is money. If you can get it done faster, you can make more money, right? But if we understand embedded systems, we understand a lot of tricks of how to make things faster, right? So there was this thing called years ago called the radio. I don't know if you ever heard of that thing. There was this AM and FM way back in the day. And what they did is they put all the complexity at the tower. They spent hundreds of thousands of dollars to make the broadcasting system to allow you to have a cheap little radio. And your radio is very simple and very easy to use. Well, how do you make your PlayStation, how do you make your phone cheaper? Well, you slow down the bus. You don't go at the fastest speed, you go at slower speed. Your laptops, everybody has a laptop that generally has throttling. Why does it throttle? Because it gets too hot. Well, if they would just give you a bigger heatsink and a bigger fan, you'd be okay. That costs money, that makes it form, it's not pretty and ergonomic, blah, blah, blah. So they sit there and say, you know, it's getting hot, we'll just slow down your processor to keep it cold. So a lot of decisions are made because of economic reasons. So they slow it down. The biggest thing they do to make something cheaper is reduce your cache. So if I want something faster, in my old computer, and I wish I still had it, I had an old Mac, and it was like a 2.0 gigahertz. It was beating all these gamer machines, right? People had Alienware, when you turn it on, airplanes change directions, the whole deal, right? And then they're like, how do you get so fast? I'm like, this processor, nobody read the specs, it has a lot more cache. Even though I'm running at 2 and you're running at 4, I'm in memory more than you are, and therefore I go faster. So it's all about the memory. And so what they do is they try to keep this stuff cheap and small. So we got to be very clever to keep it in memory, right? Alignment is very costly. If you're misaligned or if you're not in chip, it takes a lot of cycles to get the data back, right? You also have a small set of instruction cache. So you have cache for data, cache for instructions. Instruction cache is like so impossible to optimize for. Because let's say you have a for loop. You go function, 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 function. And it's like that function is in the memory. It loads into memory. This function is memory, loads in memory. By the time it comes back to the top of the for loop, all those instructions are out of memory. So to optimize code for instructions, you have to think about what instructions are being loaded and how to stay in the same instruction set longer than actually you do one call to another function, you just blew it. So instruction optimization is very hard. We won't talk about it. We'll stay away from that. So processors are not getting faster, but memory is the key. And what we want to do is try to stay inside the memory as much as possible, and that will make things faster, right? So how it originally works is a CPU has memory, and the memory was off the chip. And say this CPU is working at, I'll just make up a number, 100 megahertz back in the day. Well, then this bus might work at 100 kilohertz. So it's 100, it'd be 10 cycles or 1,000 cycles on the processor to get one cycle of data read. So once you're in the processor, it goes really fast. But once you have to go off to memory, it's a slow bus. It's a very slow highway to get there, right? So they went back and forth on this. And eventually they sit there and say, you know what? Let's move some RAM onto the CPU. So besides registers, we'll give you some RAM. Cool. And we put large memory outside of it. So once we're in RAM, it runs faster. And then that was a huge speed improvement when people moved into this. Then eventually they sit there and say, you know, we have 2 different stages of RAM. We have the RAM that's on the chip, then we have slightly faster RAM that's off the chip. This is the fastest, this is middle, and this is slow. So we put some memory off the chip, but it's much faster than it used to be. But we can't afford everything, so we'll just do a small amount of it. And we'll have even more memory outside of this. We can think of this large side here almost like a hard drive. That's some RAM. Just, we don't think of it, but it's RAM. So what happens is over time, we're like, why do we have that big chunk of memory outside? Let's put that onto the chip itself. So now we have level 1 cache, level 2 cache. And some processors have level 3 cache on the chip. That's a lot faster. Each stage is different in size. This might be 16K, not a lot, K. This might be, 64 or 256K. Then this is, your 4 gigs, right? So we have the L1, L2. And the catch here is to understand how these things work, right? So here's an analogy that really works well. You're at your computer at your desk at home. And the deal is you need books to do your homework assignment. Any book you can sit on your ass and grab, L1, right? If you have to get off your butt behind and walk over to the wall and grab a book, L2, right? Bulk memory. Shit, I need this book. I left it at home. It's in the suburbs. Hop on the road, get on the highway, go to mom's, grab the book. That's your bulk memory, right? So anything I can touch off my desk, L1, anything I have to get off my ass and go to the other end of the room, L2, anything outside the room is L3. I mean, is bulk, right? So the question is, what do I keep on my table? And there's different schemes. One scheme is, I use this book all the time. I'm keeping it on the table, right? So you have most frequently used. You might have a book that, you know what? I haven't touched this book in a while. That book can get moved to the wall. I haven't touched that book on the wall 2 months, that can get moved to mom's. So now I have like a history, how long I've used it or not used it. So you have different schemes of how you want to deal with this, right? And then what happens is, how do you match books off, books off the table into your processor? Does it directly map? So every page of your book goes into your page of your brain? Do you have remapping, scattering, reordering? So we have different ways to map that data back. So we have this concept, a cache hit. If we're looking for data and the data we're looking for is in a book that's on our table, we can access it immediately. We can just grab it and start reading it. So that's cache hit. We have immediate access, no delay, right? So if we get a cache hit, that's good. Cache miss, the data we need, nope, it's not on our desk. So now we have to see where it is. If it's on our shelf, it costs so much cycle, so we have to go get it from our shelf. If it's at mom's, we have to now drive for my mom and bring it here and bring it into our room. So it takes a lot of cycles. Cache miss are bad, right? So to refill the data, we talk about latency. How much time does it take to read it? How slow is that bus? Let's say I don't have any ebooks. All my ebooks are on the cloud, but I have a very slow internet connection. I have to wait for the book to come down. That's your latency, right? So we have latency associated with this, right? So our cache hit ratio is how much are we on average hitting cache versus missing cache? And we can measure that and kind of give you a figure of merit. Caching algorithms, least recently used. I haven't used this book in a while. It gets evicted and a different book goes on my desk. That book hasn't been used on the bookshelf. It goes to my mom's in bulk storage, right? We have most recently used. I use this book all the time. It stays, right? When I use the book, I use a ton of it a lot. So you try to put the books in there, but when I need it, I'm gonna need this book like there's no business, so I wanna keep it near hand, right? We have mapping. How do we take our main memory and move it into our cache? A direct fill that says, I read 4 lines, 4 lines go over. I need the next thing, I get the next 4 lines. Two-way associative saying each data can go in location A or location B. So I have 2 choices. There's 4-way associative. It goes into 4. So it gives more options. The key is you want to keep the stuff on your desk filled with useful information as much as possible. So direct map, well, I want that one book. And I got 3 other books I don't like. Sorry, those 3 other books lay on my table. That's direct fill. Here, I'm like going, okay, I want this book. It can go in location A or location B on my table. That's 2-way associative. So you can see when you have more choices, you can be more efficient, but each choice costs more cycles to implement. So here's the different ways we can map things. Direct mapping is the fastest. It says, I just take the next 8 books and throw them on your table. 2 ways is much slower, but gives you better caching because you can have better choices of books on your table. 4 ways even better. Then you have full associative, which is literally a little program that says which one to keep on your table, right? So this is what's going to be the best cache, but the performance, this is the fastest, this is the slowest. So we have this 2 trade-offs. One is, if we have small amount of cache, we're going to probably be efficient on making sure we have the best algorithm to put it on our table. We have a lot of cache. Well, we have a really big table, so we'll go with the easier load. So you got that trade-off. Writing to memory, right? It's really weird. This is the biggest problem. You change your variable. Now it's in cache. Does it get evicted? I'm going to change the problem for a second. You have a file system. You want to write to a file system. So you write something, F open the file, F write, you write to it. It doesn't change the file. You say write. You write to a buffer. When the buffer fills, it then writes a group of data to the file. If you say file flush, boom, the buffer gets written right there immediately. If you write to a file system and you just turn off your computer, the file isn't updated. Same process with data. We write to data. The big memory doesn't know that it changed. So it has x equals 5. You have it 3 on your cache. Now there's a consistency issue. So do you write through? Does it go through this? Sometimes it will write to a location, then it'll turn around, read it back, bring it back to your table. And meanwhile, that's getting UPS over to the wall. So there's a lot of subtleties that are happening here. So a dog's diary. 8 a.m., oh boy, dog food, my favorite. 9:30, a car ride, my favorite. 9:40, a walk, a car ride, dog food. The kids are home. The backyard's the best. The kids, dog food, mom's home, right? That's a dog's diary. Very short, very happy. Cat. Right? So it's diary of its captivity. It's not even happy, it's just pissed, right? Try to kill my captors by weaving around their feet. Should maybe try this at the top of the stairs next time. Brought a decapitated mouse to show my great power. Saw a gathering and they were talking about these things called allergies. Convinced the other captive, the dog, is a flunky because it got escaped, came back, and was happy it was back. Right? So, what's the moral of the story? Right? The dog is happy, everything's working. The cat is always trying to kill its captors and escape. Right? So we have to exploit this thing called allergies. That's our ticket, right? If we exploit allergies, we can get out of this, right? Cache. Cache is the key. We understand cache, we can make our code run stupid fast, right? All right, so instruction cache. Instruction cache is extremely hard because it has, if you go through a for loop and then you go back to the top, you already evicted it. So it's very, very hard. So we're just going to focus on data cache. Data we can control, we have a better chance of improving it. Instruction cache is really hard to deal with. It's almost not existent in how do you optimize it. All right, so L1, L2 gets evicted a lot. This week data misses basically have to cause reloading. Large functions that are using a lot of data, if it's using a lot of data, by the time it gets back to the top, the data is already evicted. So what we like is our functions to work on a small amount of data, like mad, like at a maniac pacing, like a crazy pacing. We keep using that small data a lot. Then we move to another small data and we keep using it crazy, right? We don't like large data sets. Small packages keep like data together. So we keep all of our pointers together, all of our trees together, all of our linked lists together. When they're separated all over RAM, then we have to evict and grab it and fetch it all the time. We want to align our data. We want to take our data and pad it and rearrange it so we can make it smaller. Smaller data means we can put more data packets in the cache. Right? So I'm going to introduce the hot cold data structures, right? And I came across this years ago. And what's cool is, I made this up, the hot cold, and now the terminology is used in industry. So I think a lot of them, because a lot of people I've influenced a lot of people and they spawned out from industry. So I think I got a lot of the credit for this, even though it's not in any publication. But hot cold is kind of a cornerstone to understand cache. So let's say we have a data structure, right? Double linked list, right? And this data structure has next previous, it has some data, XYZ, some other data, and a key, right? And we're going to take this linked list and we're going to look at this from a caching perspective, right? And so our mental model, just for the moment, it's not correct. It's going to be shrunk because I don't have slides that are 30 lines long, 300 lines long. I'm going to say it reads 8 D words deep. Is generally what a cache line is. So it can read 8 integers at once, right? So our example, we're going to sit there and say, ours is only 4, not 8. And it's only single line deep, not multiple lines deep. Right? And it's one way associative or direct fill. Okay. Yes.
But where do you mean 4 bytes? Like whatever the bit length, the 32 or 64?
Yeah, it's 4 D words, 4 integers. Right. So let's look at this right here. Here's our data. And we're going to start accessing data. So we look for pnex, right? So we want to read pnex. It's not in memory. So it's a cache miss. So the data is loaded from main memory into cache. When you load this, go delay, loaded, right? And what we're doing is we're looking for pnex. So we get pnex, but we get the next 4 automatically. We get pnex, previous, and x and y, right? And so when we're looking for one variable, we get 4 of them associated. We get that 4-line bucket, right? So now let's assume that we can access now, because it's in cache, any of these variables we can read easily because they're in cache. It's on our table. We can read them. So we can read next, we can read previous, we can read a y. But we want the key because we want to say, is this the node we're looking for? So we're going to walk through a linked list looking for a specific key. So it's like, oh, it's not in cache, right? So we get a cache miss. So then what we do is we evict the memory, take it off our table, right? We write it back to main memory. If we didn't change any data, we can just drop it. If we changed one variable, 1 bit, we have to write it back, right? So we evict the data. And now we want to load up the thing with the key. So we load up the next 4 that has the key in it. Load, delay. Now it's in memory. Right, so now the key is in there. We can read it. What if it's the wrong key? That doesn't match. So what would you do in a linked list? You go to the next node, right? I need pnex. Well, shit, it's not in cache now. So I have to evict the 4 words with key, and I have to reload it. So load it back. So I evict it, load up pnex. Delay. But if we only knew we needed pnex, we would have kept it. But because of the cache, we don't have it. So it takes time to load it, right? So now we access the next key, right? Crap, it's not in memory, so we evict it. Then we load up the next. And then we keep, rinse and repeat, right? So the catch is, can we do better? We're loading up data and we're like, oh, that's not right. Now load up the next pointer. Now we move to the next thing, load up that. That's not right. Load up next pointer. Switch over, load the next key. That's not right. Go load the next pointer, switch over. So there's a lot of missing we're happening here as we walk through this. So let's say we rework this data and we turn around and just put the key next to the next pointer, right? So we do that. We load up the key, we load it next to it. Cool. So we do our load from the cache, delay, 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 boom, we get 4. Now we can rekey next, previous, and a variable X instantaneous. Hey, it is the wrong key. Let's go next. It's in memory. We don't have to look at it. Because it's in memory, we have it in cache. So basically we get a cache hit. And that's a key. Because we didn't pay for that eviction, we didn't pay for that new reload, it's already in memory. This is why it's going to run faster, right? So a cache hit, crowd goes nuts, right? So then we advance to the next node. So we load up the next one. And we have next and previous in memory. We can check that. If it's correct, cool, we're done. If not, we can go to the next. Again, cache hit. So basically we just do one load and we get the next, previous, and the key in the same cache line. That alone speeds up your program by a factor of 2. Right? So say this before you go to bed. I like cache hits. Cache hits speed up my code. Cache misses make you weak, right? I like cache hits.
Oh, no.
Cache hits speeds up my code. So don't use hard coding because remember we're rearranging data so you blow up. So pretty much anytime you go plus a number, you probably are going to make dangerous code, right? All right, so hot cold structures, right? So we can see data is king, and I call this hot cold structures. Many moons ago, McDonald's came out with this sandwich called the McDLT. And the McDLT, basically they took a quarter pounder and they kind of broke it up into half. And they said, here's the bun and the hamburger, that's on the hot side. Cheese, tomato, and the other top of the bun, it's on the cold side. And then you put the 2 together, right? McDLT. So it was this styrofoam, it was a two box thing, this is monstrosity. And they spent tons of money on this, commercials, got it everywhere. And I'm not kidding you, like 2 months later, the United States goes, styrofoam ban. No more styrofoam allowed in commercial products. Like, we just invested millions of dollars in this, right? So they probably moved this off to Argentina or somewhere else. But this is the McDLT, hot side hot, cold side cold, right?
Some weird shit there.
Introducing McDonald's new lettuce and tomato hamburger, the McDLT. You get a hot side hot. You get a cool side cool. Your McDLT keeps the hot, keeps the cool. McDLT keeps the. Your McDLT could be the best tasting lettuce and tomato hamburger ever. For the great taste. New McDLT.
Right. So that's the key.
It's actually a good idea though.
It was fantastic, but then styrofoam, all the environmentalists got all pissy and screwed up a burger, right?
I'm still there like.
All right, so what we're gonna do, we can do this with any data structure, linked lists, maps, trees, it doesn't matter. The concept is still the same, right? What we're gonna do is take a linked list and we're gonna refactor it into a hot side and a cold side. The hot side is the business side, the linkages and the key. The cold side is everything else. All your bulk data goes on the cold side. So what we're gonna do is, the reason why this works is the hot side is gonna be cache friendly and the cold side will be, once you find it, there's the rest of your data. So think about this, when you're driving your car, and you wanna get to a house in a small neighborhood. You go from your house or apartment through the neighborhood and you get onto a bigger road. Then you get onto a highway. When you go quickly to that town, you get off onto a major road, then you get into the small road. Basically, what we're gonna do is go on that super highway with cache-friendly devices like next, previous, previous, looking for the key, we found it. Now we get off and go into the slow highway to go to the house. Right, so we're gonna take our data. So here's our data, next and previous. These are vectors. Vectors are 4 floats. Matrices are 16 floats. Here's 64 bytes, a lot of data, right? And I made it artificially a lot of data to show you a cache miss, that they're so big that it's 2 cache lines or more. We're breaking into hot and cold. So we're gonna have next and previous, the key, and then a pointer cold, pointing right back to it. We could have an optional pointer going back to the hot, really is not necessary really. And so we're gonna write a converter. So I'm gonna give you a linked list with these big bloated linked lists, and you're gonna convert it into a hot and cold. And we're gonna have a contest. Who can find the key fastest? So you're gonna walk the linked list, when I say walk, it's iterate. You start from the first node, next. So you start with the first one, you're looking for the node, found it. How much time does that take? Then we do the second one with the hot and cold. You go hot, found it, cold, got my data, right? Now, we're gonna do a converter. Reality is if you're doing this for your project for real, and you're doing this for a design, you would just design it correctly. We're gonna take existing crappy code and make it faster. But normally you would just design it better, right? So this is a macro, not Marco, kind of optimization. So we're optimizing larger data to exploit cache, right? So here's our data structures. And we have the hot on the top and the big bulky data underneath. Right? So let's talk about this a little more. Like here, maybe I should kind of give you a reveal and then you listen. All right, so this is the debug release. Ignore this first part here. And it takes 6 seconds to create the linked list. Right, 6 seconds to create the linked list. And that's just time. I just measure how much time it took to create the linked list, right? 6 seconds. So right here, you'll see create the bloated. We're gonna create 400,000 linked lists.
Oh, no.
I create it. You don't have to do it. So boom, here it is. And here it's like, boom, it's gonna create 400,000 of these. And it's going to call the node, which will call the constructor, which will call random set of all the data. These random these goes through other randoms, which goes to random floats. I mean, it just goes ape shit, right? And so what we're gonna do is create 400,000 linked lists. You didn't think I was gonna draw 400,000.
6 hours later.
Right? I don't think I could possibly draw 400,000. All right. Right, so these are the bloated. Right, so there's a key down here, then the next and previous. And we start with the first one, and we'll, you're not it, go to next, you're not it, and just keep going until we find it. Then what we're going to do is take this data and convert it into hot and then the cold. The hots point to the cold, and the hots then connect to each other. Right. So the key will be in these. And then this would be the cold data. There's a lot of fields, right? This is the hot. Right, so we're going to take the bloated and create the hot colds. Right. And what we can see here is it takes 6 seconds to create the list and only 72 milliseconds to convert it. Not that bad, actually. To find a node takes 9 milliseconds to find it on the bloated. But if we go down the hot, it takes 0.9. So we're 10 times faster. In debug. So in industry, if you're 10% faster, you're doing an awesome job. 20%, they build you a shrine and bring you gifts, right? I don't know what 10 times means, right? But now you're like, oh, but that's debug. What about release? 15 times faster, right? And you can see the bloated gets a lot faster because it's using the fast operations. Convert is 52 instead of 70 seconds. And the bloated is a little bit faster, because it's using more optimal code, but still the hot is faster, it wins. So that's cool. And I was thinking about this, like, actually, this is only level 1 cache. Because I have all my next and previous on my keys here. So here's the bloated, right? And here's the hot. This is only level 1 cache. Can we do better? What if we did this? We take four of these. Another 4. Loaded. Right, so. And we made a different hot. This hot is, there's the next and previous. And it has key 1, key 2, key 3, key 4. And pointer to Redirect. Just show you that in a second. And then these the 4 colds. And then this just has a pointer to each one of these. So what if I did this? There's 4 keys. And it points to another 4 keys. 1, key 2, key 3, key 4. These point to a redirect. And then each redirect points to 4 colds. Right? So when we go to the first node, boom, we check 4 keys. Not on it. Go to the next 4. Check 4 keys. It's in. That's where I used to write on marker board. I got in trouble like the first time I was teaching here. I'm drawing a graph. I'm like, here's a graph, and I start drawing across this and on the ceiling, and then they all yell at me. I'm like, we can paint it. Who cares, right? And then I realized I'm not in industry, and not the boss anymore. So let's say it's key 3, right? I have pointers here. Pointer 1, pointer 2, pointer 3, pointer 4. I just go down to the 3rd one, which then goes in this one. So now I have 2 level caching. Yes.
So you picked 4 and 4 just because like.
No, I did it because I could draw 4.
Oh,
Well, it's going to be 8 and 8.
because of how big the cache is.
Yeah.
Okay.
Be
Yeah,
8 and 8.
So
It's probably what ideally you probably do have to experiment with it, see what the right number is, but I did 8, right? So you can see here with this first one, level 1 cache. We can run through this quickly, find it, and get the memory, right? This has 2 level cache, L1, L2. Go through this, find it, boom, redirect, get to the code. Right? So let me show you the numbers of that. I had to give this a name, so I call it the Jedi. So in debug, it's 20 times faster. Right? A little more costly to convert, well, it's about the same. But 20 times faster, right? Release. I actually checked every single key and there's your answer.
But you checked every.
Right? Cache, my friends. Cache is it. If we understand cache, that's how it works, right? So the secret is, how do you make C++ fast? Memory, memory, memory is the biggest thing. I'm going to teach you other tricks, how to remove temporaries and how to make your math faster and how to do a lot of other things. But memory is probably the biggest animal. So what is the difference between new and a stack variable? I can create a class on the stack. I can create a class calling new on the heap. The stack is just a very, very fast malloc because it just moves the pointer down. A new or a heap malloc has to go find a hole and do it. So really, anything that's on the stack is going to be running a lot faster because it's a faster allocation as opposed to a heap allocation. This works because it's really fast in memory. Right? So I showed you this stuff, and this is what it is conceptually. Now let's talk about how it's really laid out. We're going to talk about contiguous, meaning they're next to each other. So when you allocate here a bloated, it just creates a bloated one, right? And then somewhere else in memory, there's another one. Then somewhere else in memory, there's another one. Then somewhere else in memory, here's another one. they're disjointed all over the place. Some go lower in address, then all of a sudden you allocate one and one's above you. Who knows? Right? That's how it's really laid out in spatial terms. So what we want to do is take our loaded and start here and count how many there are. Next, until we hit null. Right? And we say, okay, we know how many. That's how many hots we need, and that's how many colds we need. So we're going to allocate the hots together. And so we'll allocate them as an array. Let's put hot, 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 hot. And here we'll have a next points in this one, the next points to this one. So let me make this a little bit bigger. So it's going to have a next. You know, this points to this guy, this points to that guy. The previous. Right? Then it's going to point to, it will have the key. Then we'll have a pointer to the cold. Cold, right? And the cold, a big array of these, but they're much bigger. Here's this cold. Here's this cold. Here's that cold. And it's critical that the hots are next to each other. So this way, when we read this hot, remember we got 10 times faster in debug. Right, you got 15 times faster in release, right? Release, yeah, 15 times faster. So when we read one, we actually get maybe 3 hot nodes at a time, or 4 hot nodes at a time. And the reason why I get 4 of them is because they're next to each other in memory. So the hots have to be next to each other, the colds have to be next. The colds don't have to be next to each other, but it's a hell of a lot easier to do it when they're next to each other. Right? So how do we create the hots? New hot. I almost wrote hot dog. And then you put the count right there. N of them. That's why the first step is you walk through your bloated and count how many there are. And you do the same thing for the colds. So what happens is, I don't know if you remember, this is one of the Price is Right games. They have, here's all your hots. You kind of have this as your cache. When you say load in the first guy, right? Is the next, previous, key, and cold, right? You kind of get everything there. You say, so then all those are free, and then it moves down and you get all those. Then you move it down and you get all these. So you kind of get, with one cache read, you actually get 2 or 3 free hots. And because the 3 hots are sitting in RAM, it's like ding, 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 ding. You can read them really quickly, yes.
So that's really awesome when you know how many there are ahead of time. When you're doing something more dynamically.
Well, you don't know, I don't give it to you.
No. But like, for example, like, let's say you're doing a graph search, right? And you're loading nodes in at a time, like, you don't know how many you're gonna grab at once if you're like.
Okay, so what a graph search, right, is a tree, right? And my conjecture is if you have the tree laid out in memory next to each other. So remember, in a tree, it's not gonna only be the link, black, right? Was a right or left in a parent. You're gonna also have data. Don't put the data there. Put the data off in bulk area. So now all of a sudden your nodes are smaller, right? How do you walk your data? Well, when you're walking a tree, you tend to walk it from the top down. Lay out your memory top down. So create your tree and then put it into contiguous memory in the order that you walk a depth first search or something like that. And that will give you better, you get a really good cache coherency at the beginning, right? And then you'll get, you'll like miss a cache and then all of a sudden you get like, here's the branch and I get it's 2 children free. Miss a branch, then I get another node and I get it's 1 or 2 children free. And so you kind of do that. So you'll get a definite bump because it's disjointed away from your data. So this technique will work for other things. I'm just showing you not so much to say this is the way to do it. I'm just trying to show you how important cache is. That's the whole purpose of this exercise. This is completely nonsensical. Right? This is absolutely artificial. It's just for yucks, but it's kind of neat. So because we have all these and again, I don't care how the colds are, but it's just easier to make the colds next to each other for construction. The reason is if you have to create 400,000 colds, you can call 400,000 news, or you can call new array. 1. 400,000 versus 1. I will go with the 1, right? But the HOTS is where it's most important. So when you do the first cache line, you're going to automatically pay the cost for this to load, but then you go here, you look at this key, nope, here, you instantly, it's in memory. No cache, cache hit again, nope, cache hit again, nope. Now we're out of memory. So now you pay the cost for cache miss and loads up those 3 nodes. And that's how it gets faster. So it gets faster if you think about it. This moving next and previous and the key next to each other, that's a factor of 2. Right? Now, put the HOTS next to each other. It's like a 3 times 2 or 4 times 2. Let's call it 4 times 2. Say you get 4 of them. That's 8 times faster. Well, we're getting 10. All right. Right? The reason why the Jedi one is faster. When we land on 1 node, we check 8 keys. So every cache hit is 8 keys instead of 4. Right? And then once we find it, I don't try to keep this as small as possible. I don't put the pointers in there. I put the pointer in another one. So I keep the pointers out of there, just keep it smaller. Right? And again, just kind of show you the idea of this.
Is there a way to find out how big your cache lines are?
You can look up the owner's manual. No, I'm totally serious. You have to type in the chipset and the chip. Programmatically, you can kind of code this to a degree. Of course, I included the stupid thing because it's not my computer. Let's see if it's on here. No. All right, I have to put up my machine and show you the diagram, but essentially that's the hot cold. I just had a pretty picture that I'm including that I don't have with me. So instead of you get my really bad drawing here, I did it in Visio. It's much prettier. So it's same drawing, just prettier. All right. So let's talk about PA2, right? PA2 is where we're starting to deal with next performance. So when you do this, So PA2 is the first one we're dealing with performance. So unlike PA1, where I'm just happy it works, PA2, it has to run faster now, right? That's kind of the key to this. And so let's talk about this. All right, in everything we build, we'll have this little pull down here, debug versus release. It has to pass all the tests in debug and in release. Debug, I check to see, is it leaking memory? Does it pass a test? Cool. Then I'm going to only look at the release to give you your grade. But I take the lower of the two. If 10 tests pass in debug and 3 pass in release, you get 3. If 10 pass in release and 2 pass in debug, you get 2. So the idea is the debug is really just your safety, it's your development, but what counts is the release, but you do need to check both of them to make sure they work. So PA2. Has a couple problems. So the first problem is, I think the easy part, but some people think it's the harder part. The first problem, remember you have to make sure you validate both the debug and release. You're going to take this data structure rework and you're going to rearrange it to make it smaller. So just like we were doing with our alignment, right? And so here it is, here's refactor, alignment problem, rework. Here's our data. How would you rearrange this data to make it smaller? And you rearrange this data, so you go in here and modify this, go and rework, and there's no way around it. I show you the answers. So you'll know if you're right, because there's the answers, right? So you rearrange things and those are the numbers you'll get, right? So that's easy enough.
So that one you're literally just looking at, like, let's say like that first example, just 3 lines, just reorder them.
Reorder them.
Just- Okay. That's okay.
Right.
Cool.
And then whatever you have as padding, make it explicit, you know, to say char pad.
Right.
That's really it, really easy for that one. So that one's a freebie. This next one is, I'm going to give you sample code or sample data. And I want you to write, because you guys are super smart. See like how I'm buttering you up for the fall. I want you to write a program to find the data alignment of the structure and to show me the alignment padding, right? So this is what it will look like. Data structure A. Here's address 0. You see 0, 0, 0, 0, AAA. Right? I need you to mimic this byte for byte. It's hard for me to compare it, so you're going to mimic this. So this becomes an exercise of how good are you at printing. So I remember I was chastising some poor student using cout. You can use cout or printf, but the function has a signature, you have to match it. I would use printf because printf is 1,000 times easier than anything I know. So here's the function. I'm going to take memory and blast AAs into it. Then I'm going to do placement new, that data structure, and you're going to print it out, right? And here's the print me, passing the pointer to it, the size, and then here's the string, and you fill in the magic. And here's where we're going to use trace out to. So trace out to is the same as trace out. Or the same as printf, sorry, printf. You want to use trace out to. And just match this, this output. So you're going to get a pointer to the raw data, the size of the structure, and then that string. And so we look here, the string is going to be data A, I think, right? Yeah, data A. And then you're going to add the colon, new line, 0, 0, colon, now you're gonna read the data, print it out. New line, 04, read the data, print it out, and just keep on going. So let's look at E for a second, right? Data E. Data E. Here's E. And what's interesting with E is using A. Here's A up here. So what you need to do is add to this a default constructor, initialize the variables to 0, right? Because otherwise it would just be noisy. And this way it will match it. And then what this is going to do here is for E, it's going to do the default constructor for A, the default constructor for C, add padding before or after char, add padding before or after B, and then here's this, and this output for this variable, so I'll just put this up here, is literally there. That's what this will look like. And this is going to help you understand what gets called first, what gets padded, all this other stuff. So you can see, here's A, right? A, there's A, here's A. A gets dropped right here. So we can always do this by hand. Here's A, boom. And then we're gonna drop in C next, C. C's alignment, right? Here's C. And we can see, look, there's this data right here, right? So what the hell is going on? Why is this way? I think I copied C, right? C. I'm sorry. That's right. Let's see. So now, if there's no padding, boom, they get stuck together. Now it's character AA, so put that in there. So there'll be 0. Now there's going to be some variable padding before we get to B. Here's B. Right. Now we can see here, there is 2 sets of full zeros here. Sorry. So you're going to slowly reverse engineer what's happening here. I'm having a hard time doing it all by memory, but you see the output. Okay, I think there was a question about the printing. So we print this out. All right, so now let's look at, that's just your linked list problem. So now we go, that's your alignment. So now your linked list problem. All right, you're gonna refactor this and you're gonna basically create these 4 functions or 3 functions. Find the key, hot, cold, and bloated, hot, cold, right? So the find key. So in here, you're gonna do the find key. You have to pretend, because this is for the bloated, you have to pretend it's a linked list. So you do a while loop, next, found it, break, right? This has to be in an iteration with linked list and a while loop. If you use array indexing, a for loop, wrong answer. If you ever use a for loop walking on linked list, you should get fired. That just says, please fire me. I have no clue what I'm doing. Always while loops with linked lists, right? If you don't do it, I'm going to knock you off a point. So then your hot cold, right? You're going to create the hot function right here. And cold, let's go with this. you're gonna take a bloated linked list and create the cold out of it. You're just gonna pointer to the bloated. What's on the bloated? Here's the bloated. There's a pointer to the head. So you don't even know how many there are. So the first thing you need to do is walk the linked list saying next, count. Like, okay, I counted 10,000, 400,000, whatever. Now you know how many to create. Now your job in the hot cold is to do the nodes for hot cold. So now you're gonna put a pointer to the hot and a pointer to the cold. And update that. And fill in all the data. Right? Then there's going to be a destructor. So however you constructed this, you have to undo it here. So if you created 2 array news, you better do 2 array deletes. Right? So you have to kind of fill that part out. Then you are going to find the linked list. So you start at the hot, you go next, key, found it, return the cold node. Right? And if you found it, return true. So now let's look at the linked list code. Here's bloated. And don't worry about this. It's there for medical reasons. All right. I'm going to create a linked list of 1,000. And then you're going to go hunt for this key. And when you find the key, you return the pointer to it found. And I'm going to compare every variable to it. It was horrible. Right. Then I'm going to ask you, go find this key. And like I said, you guys have it easy. You just write code, man. I wish I could just like do your stuff. And then I'm going to check it. And I'm going to check it again. Now I'm like going, I think and again, I think you successfully done link, find key. I think you found it. And I'm going to give you a number that doesn't exist. You better not return true. So I'm just checking that too. Right? Next one, I'm going to create 1,000 nodes. And you're going to get a pointer to it. And you're going to create the hot cold. Then I'm going to call your function find. And you're going to return the hot cold pointer and the hot pointer and the cold pointer. I'm going to check the cold. I'm going to check the hot. Hot's easy. There's only 4 links. Next, previous, key, and cold, right? And I keep checking the cold and cold and cold and cold. Right? Then I will give you another piece of data and I check it again, right? So this feels pretty good. And so you get the drill, right? Now we go for, now you're going to find a cold. I create another linked list, find the cold, find the hot. What the hell am I doing here? Let's do next week.
Saturday.
Next week's.
Yeah, everything's on Saturday. I don't know what the hell I'm doing here, but I know it's something important. I have to reverse engineer my own code. All right. I think I'm checking. This checks to convert. This is still hot cold, I think. No, I don't think I'm in. Jedi. No. Convert. Let's convert. Oh, so this is checking to make sure that your hot colds are linked correctly. So I'm checking the links between your hots. Make sure they're not circular, make sure they terminate correctly, and kind of process correctly. All right. Yeah, I'm sneaky. I have you find nodes that I know happen to be next to each other, so then I can check the pointers to see if they point to each other. Yeah, pretty proud of myself. All right. Then the last one's the timing. I'm gonna sit there and say create 400,000. You're going to, I'm gonna time it. Then I'm gonna verify that I found the right node. Then you're gonna convert it, but I'm gonna measure how long it takes you to convert. And then I'm gonna have you find it. I'm gonna measure how long it takes you to find it. And then I'll verify it and store off the data. Okay. Then we go to the Jedi. So now the Jedi problem is here's our node, right? Blue. Here's our cold. You're gonna have a hot, a cold, but you're really gonna have a hot, and you're gonna have a redirect then a cold, right? So let's look at this, a hot node, where's hot? Hot will have next, previous, and an array of keys. In this case here, 8 keys. Then your redirect is going to have an array of 8 cold pointers. So if you found index 3, you then go to redirect and go to index 3 and you got the pointer.
Oh. So they link through the redirect keys then.
Yeah, because remember it's 2-stage.
Oh, right, because you have the.
Yeah, it's 2-stage. So you find 3, then you go down to 3, and that gets you to the pointer to the cold.
Oh, can I get?
Now, otherwise, if I would have put the pointers in there, then my hot node would be really big,
Yeah, that's not.
and I wouldn't get much of a performance increase. Right. All right, so that's it. So same shake and bake thing. You're gonna create the hot cold Jedi. This is how you delete a hot cold Jedi, and this is how you find a hot cold Jedi. Same pattern, shake and bake, right? So here's the first one. I do 1,000. You convert it, and then I go nuts and check things.
So for each one, we have to convert it to a hot cold still.
Yeah, well, no, to a Jedi hot cold. This one's to a Jedi hot cold.
Can you go back, just which function is that? It's just, oh,
It's constructor.
it's just the constructor that converts it.
Yeah, constructor does conversion.
Oh,
Yeah, and all you get is the pointer,
yikes.
right? So then you do this. And then you find the key. The last one is timing. I give you 400,000. You convert it. Oh, I find my 400,000 traditionally. Then I find convert it, and I time you on how long it takes to convert in Jedi land. Then how long it takes you to find it in Jedi land.
Are you caring much about the conversion time, or do you care more about
Yes.
the, okay,
Yeah. No.
can I just,
Yeah, does timing count now? Yes.
yes, it does, yes.
The operative word here is optimize C++, not good
True.
enough C++.
That's fair, yeah, fair.
Take my time.
Yeah.
So, and you know, just to kind of just remember that and that's this assignment. So here. But it I'll show you that our times turn out to be pretty good. Now, if how it works, I run all my machine. I'm giving you my times on my machine, right? Your machine may be slower, maybe faster, right? The problem is I don't have your machine, right? So I don't know how fast your machine is, right? Some people have screaming machines that, you know, like are, you know, crazy gaming platforms. Some people have cost-effective, efficient machines. Just to tell you, if you do the technique right, you'll get full credit. I had a student who was totally freaking out. She's like, my code is like 5 times slower than everything you do. And she won. She was the fastest at every single homework assignment and won the particle system. The poor thing was comparing. And so the whole time, I think she's beating herself up like, oh my God, it's so slow. So she's trying to like get every single speed increase because her machine was slow. And I think that might have indirectly motivated her to be a better programmer. But she clobbered everybody else.
Jeez.
Duplicate clobbered it, right? So what you do is this. You run it. And the best thing to run is you run the fine, the bloated fine, because bloated fine is pretty straightforward. And you say, Ed gets 9, what do I get? If you get around 8 or 10, it's the same. Call it close enough to be the same. If yours is 20, then you know that every number is 2 times. If you're 5, every number is a half, right? So you just take this as a benchmark, right?
So the ratio is what.
The
really
ratio is a big thing. So that's why I always kind of print out the ratio to give you an idea. Now, the ratio is kind of a false. The ratio makes sense if we're comparing apples to apples on the same machine. If I take everybody's code, run it on my machine, and I compare the ratios, there it is. But you get to create the bloated find, right?
Oh,
So, give you an example. So here's my code. Do we have enough time? Yeah, we have enough time. Ratio is not. Ratio is only good as if you do it correctly. If you sincerely do the fastest search you can do, you get good ratios, right? So here's mine. On this machine, so it's gonna be really dog slow because I'm recording and blah blah blah. I have 1,000 things open. Oh yeah, this is the beauty I got last week. The machine here, the teaching machine is out of date, so it doesn't have the latest libraries. One way to do it, huh?
I guess.
Bastard. All right,
Can we do that?
yeah, you could do it, but I'm gonna grade it as if it wasn't there.
Bummer.
Like put in big bold letters, do not modify.
Yeah. See this one. It's smart enough to cut it. Ah, shit. All right,
You forgot to close brace on 28.
Oh, yeah. That would do it.
if you guys look at the stuff, it's just insane, the framework stuff. I get confused by my own mess I made.
Yikes, 6 seconds. Oh boy.
All right, so this is not bad. This machine's not bad. All right, so it's taken 8, the ratio is 8, and my find takes in 15 milliseconds, right? Now right. Hold on a second. It's one Google away. I know. Hack here. It's going to do it correctly, but let's just do it incorrectly. So my ratio is about 8, right? $137 now. Right, so ratios don't believe ratios because I just dog my find to make my ratio better. Right, so what happens is when I grade it, even though you get a ratio, what if you did your fine, because you get to write the fine function for hot and cold, and you have to write the fine function for bloated. And if you do a really slow bloated, my God, your ratios are fantastic, right? Look, 137 in debug, I'm a king, right? No, I dogged the system, I totally cheated. So what I always do is when I grade this, I grade on milliseconds. So the ratio is there to help you kind of give an idea of the figure of merit. But when I grade, I actually grade milliseconds. So then I would say, oh, this is 164. This is a ratio of 8:1. So, that's it. And so how the grading goes, and I don't know, because what I do is when I run my machine 10 times and I record all the numbers. And I sit there and say, okay, I'm getting, let's just pretend I'm getting 10 milliseconds for hot, cold, in debug, in release, let's say release, I'm getting 15. And then I'm getting 50 ratio in Jedi. And I'm getting 72 milliseconds for convert. Right? So this is what I get. So I would sit there and say, you know what, if anybody got 8 or something, I'll give you full credit. So if you get greater than 8, so you get, anything greater than 8, you get 2 points. And if you get 4 to 8 milliseconds, you get 1 point. And if you get less than 4, you get 0. Ratio. So I'm taking my speed and kind of knocking it down and then comparing you on a scale. So basically I give you 2 points for speed for the hot cold and 2 points for speed. And, and this gives you another, 2 points for speed. So there's 6 points just related to speed, and the rest you get a point for every unit test. And that's how it works. And what I do is I don't want to, you don't have to match my score. I take my score and kind of knock it down and say, okay, this range gives you this range gets this. So if you're doing the right technique, you'll get full credit. Yes.
So for the bloated, are you creating the bloated?
Yeah, I created.
Based on the bloated header that was in there?
Yes.
Oh, okay. So then we have all the data that we would.
You have everything. All you're doing is converting.
Oh, all right.
Yeah, you're not doing anything. Now, some people realize like, oh my gosh, I like this like student think I wasn't going to catch this. I started with a linked list, and it goes through 378,000 nodes. And found it, that's it, right? One student goes, oh, I'll just start a pointer here and work it backwards, right? That's against the spirit. Clearly, you want to walk the linked list as a linked list. They're like going, oh, it's an array because your memory is laid out in an array. So they use a for loop. They use bracket operators. 0 because it's supposed to be a linked list. So we're trying to compare linked list to linked list with a different layout to show you the caching benefits. Like I said, this is completely contrived. It's just for fun. But you can see that cache does affect performance. Okay, that's really it. I'm glad I got through this. Questions, problems? We still have 15 minutes if you want. Go through.
I was gonna ask, so when are you gonna post on the Perforce?
Tonight. So everything is due Saturday. Oh, forgot to tell you how to submit and assign your homework. All right. So is anybody done with their PA1? I'm just gonna pick on my friend there because I have this stuff laid out. All right, so this is how you do verification. All right, you go to your machine. So let's do a git. And this is critical. If you give me garbage, I grade garbage. And then you're like, it doesn't work. Sorry, you gave me garbage. I don't have your machine at home. you know, so you don't have access to it. So you gotta make sure you check it in correctly. So it's really simple. There you go. So first thing you do is work on your machine, on yourself, right? You try it out, you're like, okay, cool. And we compile it. Run it. And we get into hold on a second. I'm getting bit by the mystery.
Oh, good, because I was about to go, shit.
No, it's this one again. I gotta figure out. They won't upgrade it here. That's the rub. They won't upgrade it from. So clever to making all these tricks. So I always joked about, my one friend does data mining, right? And I said, you're gonna create a tool that's so smart, you're gonna give it to the FBI and then they're gonna arrest you. Like, no, they're not. Like, watch, they're gonna arrest you. Because you're gonna write it and then it's gonna, the computer's gonna be mad and it's gonna attack you. All right, boom, 8, right? So yay, 8. All right, so this is what we do. Exit this. Completely, right? And then exit this, and then what we're gonna do is copy this over. Why did we copy this? In case something bad happens, right? We don't have to copy it. If you don't want to copy it, go here and right click on it. And just write down safety. Again, in case something bad happens, right? So now you go back to Perforce. See, now it won't let me because we'll do the copy. All right, so then what we're gonna do is go here and delete it. Hopefully it'll let me delete. No, you won't do that for me, will you? Must have something open with it.
Perforce, is perforce count?
No. Sometimes DePaul added a very insanely evil virus scanner. And the virus scanner holds the thing too long. It holds the file when you open it. All right, so let's go back to this. All right, so here we delete it. Delete. Cool. All right, now we go back to Perforce. And now I go back to here, PA1 on Depot. I right click, this is critical, and you go get revision, force operation, force. And this brings it down. Again, forcibly every file. Boom. All files are down. Now, I have to do a correction here because I have to foobar his project sentence. So let me just pretend that's correct. Yeah, see, I corrected. All right. So you just pretend you just did the grab. Boom, it brings down, right? Now, all you do is this. You go in here, double click solution, don't click anything else. And then what you're going to do is compile and run it. Do not check stuff out. Do not hit clean me. Just hit compile. Run it. If you're happy with this grade, that means what was on the server was correct. So now everything's cool. Now we're going to do the PDF. Now you go to the PDF and you check it out. Right? So you check out the PDF. You go in here and you're gonna put in the build number, right? And so here, in this case here, the build number is, we go to Perforce, and we take PA1, and we open up this thing called submitted change list. And all we do is drag PA1 over, boom. And there we go. And we can see here, here's all the change lists. Grab the largest number, 14, 6, 1, 4, 1, 6, 3, 6. You put that in there, and then you submit this in and you're done. Obviously, you click, did I cheat, yes or no? And you just verified the bill. A lot of people will click this out of habit. They'll keep clicking, hey, it's working. I trust you. You say it's working, it works. If it doesn't compile for me, you'll find out because it doesn't compile, right? So just go through this. If you do this, it will guarantee to work. Right? That's it. So please verify before you check in and submit.
Would you be able to put a Piazza note about this? So we
Oh,
can go
you mean
back
like
to-
the one that's there?
Oh, is
Yeah,
that
you already
already?
did. I was
Wow.
just thinking, didn't you
Really?
just put
Wow,
this on there?
I did not realize.
I mean,
that.
there's so many messages.
I know, that's
No,
probably-
there's
I probably
nothing.
overlooked
This is
it.
really, you guys are really quiet right now. Yeah.
Oh,
Verify
Oh,
for person.
yeah.
And
That's
I've
why.
never seen that.
Okay. I
And
overlooked.
oh,
it.
by the way, here's a video.
Cool.
And the
Perfect.
video from the lecture.
Alright, so,
Perfect.
it's
I
there, it's
overlooked
pretty,
that then.
pretty good, so.
That's
Give it a try, you'll get there. So it's due Saturday night. I have grade Saturday morning at sometime after 7 AM. So that means if you're still cranking out at 4 AM, don't worry about it, just get your shit checked in. Then how it works is if you met with an advisor, I mean tutor, this week or next week, that's it. Send me the time and the person you met with. I will regrade yours with no penalty next week. So you get 2 bites at this apple. Otherwise, if you do nothing, everybody gets a free regrade on all the PAs at the end of the quarter. It just has a 30% hit. So no matter what happens, like let's say, oh my God, PA2 went belly up. You get a 0. Redo it between now and week 10, I'll regrade it and give you a new grade. With, 30%. So this way you got time to do this stuff. If you haven't met with a tutor and you're struggling, probably God told you should meet with a tutor. A lot of people go to tutor even when they're doing well, and they're like, okay, now I understand even better why it works or doesn't work.
Makes sense.
You guys will get there. Just hang in here. This is the struggle part. You're drinking from a very, very strong fire hose right now. But remember, next week you're a Jedi. Right? So that'll be cool. All right, be safe out there. See ya.
Have a great night, everyone.
For 3 hours is
Oh, I know.
not good for your legs.
Oh, I know, trust me.
So,
You're done. You got that working.
yeah, very excited about it. So actually.
I am intending to try to finish it tonight.
I mean, you got the core working.
Yeah, I
The
didn't
only thing
realize
that's
what it was.
different is that the scan
Was actually doing
has-
that calendar.
for the,
Oh, it's in Mexico City.
Yeah, that's what I'm
remove
going.
gives you
Oh,
the
shit.
name, so you're just
Yes.
gonna iterate through.
Oh, yeah, okay.
I
Oh
mean,
my God.
you've been iterating. through
You're like, you're gonna go
Yeah.
next week. So,
No, I'm
The
actually
teacher
going to
structure
Mexico,
is
so like, what is that like museum? I wanna
The
go.
ad is
We're already
exactly
planning on going to the
the
Freedom Hollow
same.
Museum.
If you might have a memory week, you might need to delete.
there's 2.
I forget where it was.
There's the Freedom Hollow.
I'm
There's
gonna,
another ad, but
I wanna try to do it on my own.
Yeah.
I don't. need to
that's
make
what
that
that-
mess.
So
Anthropology?
anthropology is one, and there's another one that has a
I
sign.
really don't care when people.
I know, I just.
Like,
I don't want it to come off
Oh,
that way,
yeah.
you guys, but
I
it's just like,
understand.
hey, I enjoy talking through it,
Yeah.
and it helps.
No, like I'll be talking out loud to my roommates. I'm doing my workout. What the fuck do you even say?
Yeah. Oh, so it's the Anthropology Museum.
Here, let's just make sure. Yeah, so there, you can see, look at this.
Yeah.
That's how big it is.
That's amazing. Yeah, okay, I'm adding it to the list.
Yeah, oh my gosh, you go in there, it's like, it's colossally huge. Where are you staying?
In Condesa.
Okay, you know that area really well.
Yeah, I'm psyched. I'm very excited.
Okay,
But anyway, the reason I bring that up is because about deadlines. So I'm gonna start this as soon as I can.
Yeah.
I just got hit with, I'm in the intro to AI class, which I was told was easy, and I just got hit with an assignment that I'm pretty sure I bit off more than I can chew. So I'm just wanted to give you the heads up if I'm a day late, I'm like preemptively asking for the extension.
Well, see where you're at.
Yeah.
Because I think you'll come together.
I just, that
Okay,
whole week
so-
I'm gonna be
so,
traveling.
Have you been to Mexico before?
No.
Okay, I used to work there with the cartels and kidnapping and killing, right?
Yeah.
Here's the deal, no bullshit. You do not take a taxi, public taxi, ever,
Never.
never. What you do is the hotel or the B&B you're staying in, you call them, you say, I need a taxi from here to here. That's it. Do not take one off the street.
No,
I'm like, can't be more serious about this.
noted.
Still going.
Yeah, is Uber safe? Do you know?